Welcome, wanderer of the atomic frontier, to a journey through 7 decades of powered protection that shaped the wasteland we know today. Tonight, we explore the complete chronicle of power armor, from desperate scrap metal cobbled together by raiders seeking any edge against the harsh realities of survival, to technological marvels that represent humanity's greatest achievements in protective engineering. These mechanical shells have sheltered soldiers, workers, and survivors through the darkest chapters of human history. So settle in, make yourself comfortable, and let your mind drift as we traverse the evolution of powered combat armor together. There's no need to remember every technical specification or historical detail. Just let the story wash over you like radiation settling into ancient metal, steady and persistent in the silence of the wasteland night. Close your eyes when you're ready, and let's begin our chronicle with the most desperate of all armored solutions. The scrap that raiders call power armor tells the story of human desperation written in rust, blood, and the stubborn refusal to surrender to extinction. In the decades following the Great War, when civilization had crumbled into radioactive dust and the strong preyed upon the weak with methodical brutality, those who chose violence as their path to survival faced a fundamental problem that would define their existence. The wasteland was full of things that could kill you faster than hunger or thirst, and leather jackets offered little protection against the claws of a death claw or the plasma rifle of a better-equipped rival. Raider power armor represents the absolute bottom tier of powered protection. But understanding its origins requires understanding the psychology of those who created it. These were not engineers working with unlimited budgets and access to pre-war manufacturing facilities. They were scavengers, murderers, and psychopaths who had chosen brutality as their survival strategy in a world that rewarded such choices with continued existence. When a raider gang discovered the twisted wreckage of a military convoy, or stumbled across the rusted frame of power armor abandoned since the bombs fell, they saw opportunity where others might see only scrap metal. The construction philosophy behind raider power armor was brutally simple: function over form, intimidation over protection, and immediate utility over long-term reliability. A typical raider engineer, usually someone who had learned welding and metalwork through necessity rather than formal training, would approach a power armor frame like a canvas for their particular brand of wasteland artistry. They would strip away damaged components without understanding their function, replace sophisticated alloys with whatever metal happened to be available, and modify systems they could not comprehend through trial and error that often ended in explosive failure. The results were as varied as the gangs that created them, each suit reflecting the personality and resources of its builders. The disciples, known for their theatrical cruelty and artistic approach to violence, would decorate their armor with spikes, blades, and the bones of their victims, creating walking monuments to their chosen lifestyle. The operators, more pragmatic in their approach to criminal enterprise, focused on functionality and reliability, producing armor that was crude but effective for their business needs. The pack, embracing their animalistic identity, would incorporate animal pelts, claws, and teeth into their designs, transforming power armor frames into mechanical predators that reflected their pack mentality. But beneath the surface modifications and cosmetic additions, raider power armor suffered from fundamental flaws that no amount of welding skill or scavenged materials could address. The servo motors that provided the strength enhancement essential to power armor function were delicate mechanisms requiring precise calibration and regular maintenance. Raiders typically lacked both the knowledge and the tools necessary for proper servo maintenance, resulting in suits that provided little or no strength bonus despite their impressive appearance. The hydraulic systems that enabled fluid movement became clogged with dirt, debris, and improvised lubricants that corroded internal components over time. The power systems were perhaps the most problematic aspect of Raider modifications. Fusion cores, the standardized power cells that had been designed to provide reliable energy for sophisticated pre-war systems, were forced to power jury-rigged electrical systems that drew power inefficiently and created dangerous feedback loops. Raiders would bypass safety protocols they did not understand, remove redundant systems they considered unnecessary, and add power-hungry modifications without consideration for the electrical load they were placing on aging fusion technology. The result was suits that drained power cores at accelerated rates while providing inferior performance compared to properly maintained military hardware. The armor plating itself told stories of desperation and resourcefulness that would have impressed pre-war engineers if they could have overlooked the complete absence of proper metallurgy. Raiders would weld steel plates salvaged from cars, buildings, and machinery onto power armor frames, creating patchwork protection that was heavy, poorly distributed, and often weaker than the original armor it replaced. The weight distribution problems created by improper plating modifications put additional strain on servo motors that were already struggling to function with inadequate maintenance and jury-rigged power systems. The tribal variants of Raider power armor pushed improvisation to its absolute limits, incorporating materials that had no business being attached to sophisticated military hardware. Wood planks, animal hides, scavenged plastic, and even concrete blocks were welded, bolted, or tied onto power armor frames by groups that had regressed to pre-industrial technology levels while somehow maintaining access to fusion-powered equipment. These modifications were testament to human adaptability, but they transformed precision military instruments into crude approximations of their original function. The psychological impact of wearing Raider power armor extended beyond its practical limitations to encompass the identity and social dynamics of Raider culture itself. For many Raiders, their armor represented not just protection but status within their violent community. The most elaborately modified suits belonged to gang leaders and veteran fighters who had survived long enough to accumulate both resources and reputation. Young Raiders would spend months planning modifications to their armor, viewing each addition as a step toward greater recognition and fear from both enemies and allies. The intimidation factor was often more important than actual protection for Raiders who relied on psychological warfare as much as physical violence. A Raider gang approaching a settlement in power armor, even crude and poorly maintained power armor, presented a threat that most civilian defenders were psychologically unprepared to face. The mechanical silhouette of powered armor triggered pre-war fears and associations with military might that could break enemy morale before the first shot was fired. For Raiders who lived by inspiring fear in their victims, this psychological advantage was as valuable as any physical protection their armor might provide. But the true tragedy of Raider power armor lay not in its technical limitations, but in what it represented about human potential squandered by circumstances and choices. Each suit contained components that had been designed by some of the most brilliant engineers in human history, powered by fusion technology that represented the pinnacle of pre-war achievement, constructed from materials that had required decades of research and development to perfect. In the hands of properly trained technicians with access to appropriate tools and replacement parts, these same frames could have been restored to their original specifications and used to protect settlements, explore dangerous areas, or perform the heavy labor necessary for rebuilding civilization. Instead, they became crude weapons platforms for individuals who had chosen predation over production, violence over cooperation, and short-term survival over long-term planning. The raiders who wore these suits were not inherently evil, but they were products of a world that had rewarded brutality while punishing weakness, that had offered few alternatives to those who lacked the education, resources, or social connections necessary for legitimate survival. Their power armor reflected their circumstances, functional enough to serve immediate needs, intimidating enough to support their chosen lifestyle, but fundamentally limited by the knowledge and resources available to its creators. The maintenance challenges faced by raider armor users were severe and often fatal. Without access to proper diagnostic equipment, technical manuals, or replacement parts manufactured to original specifications, raiders attempting to repair their suits relied on trial and error methods that frequently resulted in catastrophic system failures. A servo motor pushed beyond its design limits might seize during combat, leaving the wearer trapped in several hundred pounds of immobile metal. A power system modification might create an electrical short that electrocuted the operator or caused a fusion core to rupture in a miniature nuclear explosion. The legendary unreliability of raider power armor became part of wasteland folklore, with tales of suits that worked perfectly for months before suddenly shutting down at critical moments, armor that provided excellent protection against bullets, but fell apart when exposed to rain, and modifications that seemed brilliant until they exploded without warning. These stories reflected the fundamental truth about raider engineering. It was reactive rather than proactive, focused on immediate problems rather than systemic solutions, and constrained by the limited knowledge and resources available to people who had never been intended to maintain such sophisticated equipment. Yet, despite all their limitations and dangers, raider power armor suits continued to proliferate throughout the wasteland because they served a fundamental need that transcended their technical shortcomings. In a world where survival depended on the ability to project strength and defend resources against constant threats, even crude protection was better than no protection at all. A raider wearing a malfunctioning suit of power armor was still more likely to survive an encounter with wasteland predators than one wearing only leather and metal scraps. The psychological boost provided by wearing power armor, regardless of its actual effectiveness, gave raiders confidence that translated into improved combat performance and better survival outcomes. The evolution of raider power armor reflected the broader trajectory of post-war technology development, where sophisticated pre-war systems were gradually degraded through improper maintenance and modification until they bore little resemblance to their original design specifications. Each generation of raiders inherited armor that was slightly more corrupted than the previous version. As knowledge was lost and expedient modifications accumulated over time, the process was one of technological entropy, where complexity was gradually replaced by simplicity as understanding diminished and resources became scarce. But within this decline lay seeds of eventual recovery, as some raiders possessed natural mechanical aptitude that enabled them to develop genuinely innovative solutions to common problems. The most skilled raider engineers would eventually abandon their violent lifestyles to become legitimate technicians and mechanics for settlements that could offer them better lives than constant warfare and scavenging. Their experience with improvised modifications and field repairs, while crude by pre-war standards, represented valuable practical knowledge about maintaining complex systems under adverse conditions. The legacy of raider power armor would persist long after its creators had been killed, reformed, or absorbed into more stable communities. The modifications and repair techniques developed by raider engineers would be studied and refined by later generations of wasteland technicians who possessed better resources and education. The psychological lessons learned from raider intimidation tactics would influence the design and deployment of power armor by organizations like the Brotherhood of Steel, who understood that appearance and reputation were as important as technical specifications in determining a weapon system's effectiveness. Most importantly, Raider power armor represented proof that human ingenuity could not be completely suppressed even under the worst possible circumstances. The same creative intelligence that had originally designed power armor continued to exist in the minds of people who had been forced into lives of violence and desperation by circumstances beyond their control. Their crude modifications and dangerous repairs were testament to the persistent human drive to improve one's situation through applied intelligence and determined effort, even when the odds of success were minimal and the consequences of failure were severe. The T-45 power armor represents humanity's first desperate attempt to level the battlefield against forces that conventional warfare could no longer address, born from the resource wars that consumed the world in the decades before the Great War transformed desperation into necessity. When American forces found themselves facing Chinese-powered infantry and armored divisions that could shrug off small arms fire while delivering devastating counterattacks, military planners realized that sending unaugmented soldiers into such engagements was tantamount to organized suicide dressed up as patriotic duty. The development timeline of the T-45 began in 2065, when reports from the Alaskan front made it clear that American conventional forces were being systematically outmatched by Chinese military technology that had leaped ahead during the resource conflicts. Chinese-powered armor, while inferior to what would eventually become American standards, was sophisticated enough to turn individual soldiers into walking tanks capable of destroying entire squads of conventionally equipped infantry. American military leadership faced the uncomfortable reality that their technological superiority, which had been taken for granted since the Second World War, was no longer guaranteed or even probable. The crash program that produced the T-45 was characterized by urgency that bordered on panic, as Pentagon planners calculated casualty projections for continued conventional engagements that painted pictures too horrific to contemplate. American soldiers were dying at rates that made previous conflicts seem like training exercises, not because they lacked courage or skill, but because they were being asked to fight opponents who possessed fundamental technological advantages that rendered conventional tactics obsolete. The solution required nothing less than a complete reconceptualization of what an individual soldier could become with proper technological augmentation. West Tech Corporation, already involved in advanced materials research and military applications development, received contracts that represented blank checks for developing powered combat armor that could match or exceed Chinese capabilities. The technical challenges were immense, requiring breakthroughs in metallurgy, hydraulics, power systems, and human-machine interface design that pushed the boundaries of what late 21st century technology could accomplish. The servo motors alone required precision manufacturing that existed at the absolute limits of pre-war industrial capability. The first prototype T-45 suits were crude by later standards, but revolutionary for their time, transforming ordinary infantry soldiers into powered warriors, capable of carrying and firing weapons that had previously required crew-served mounting systems. A soldier wearing properly functioning T-45 armor could lift and aim a minigun single-handed, absorb rifle fire that would have been instantly fatal to unprotected personnel, and march through terrain that would have stopped conventional infantry entirely. The psychological impact on both American troops and their enemies was immediate and profound. The materials science behind T-45 construction represented some of the most advanced metallurgy of the pre-war period, combining steel alloys with composite reinforcement that provided protection against both kinetic and energy weapons, while remaining light enough for servo-assisted movement. The armor plating was designed in overlapping segments that allowed flexibility while maintaining structural integrity under combat stress. Each plate was precisely shaped to deflect incoming fire while providing mounting points for the internal mechanisms that made powered operation possible. The servo motor system that provided T-45 wearers with enhanced strength was a marvel of miniaturization and precision engineering that required manufacturing tolerances measured in thousandths of an inch. These motors had to provide enough torque to move several hundred pounds of armor and equipment while remaining responsive enough to translate the wearer's movements into fluid mechanical motion. The hydraulic systems that supported the servos operated under pressures that would have been dangerous in less sophisticated applications, controlled by mechanical computers that processed movement inputs faster than human reflexes could detect. Power distribution throughout the T-45 system relied on fusion cell technology that was still experimental when the armor entered production, creating reliability issues that would plague the platform throughout its service life. The fusion cores that powered T-45 operations were miniaturized versions of technology that had previously required entire rooms to house, compressed into backpack-mounted units that provided portable nuclear power for sophisticated military systems. The energy requirements of full-power armor operation meant that fusion cores had limited operational life under combat conditions. The heads-up display system, integrated into T-45 helmets, represented the cutting edge of battlefield information technology, providing soldiers with targeting assistance, ammunition counts, system status indicators, and tactical data that had previously been unavailable to individual combatants. The display overlaid crucial information onto the soldier's field of vision without obscuring their ability to observe and engage targets directly. The targeting computer could track multiple enemies simultaneously while calculating optimal firing solutions for various weapon systems. Environmental protection was a crucial aspect of T-45 design, as the armor was intended for deployment in conditions ranging from Arctic warfare to nuclear battlefields, where conventional protective equipment would prove inadequate. The suit provided complete atmospheric isolation with air filtration systems capable of removing chemical contaminants, biological agents, and radioactive particles from ambient atmosphere. The thermal regulation system maintained comfortable internal temperatures despite extreme external conditions. Training soldiers to operate T-45 armor effectively required completely new military doctrines and educational programs that transformed conventional infantry into powered assault troops. The psychological adjustment to operating in power armor was significant, as soldiers had to learn to trust servo-assisted movement while developing new situational awareness appropriate for their enhanced capabilities. The physical demands of power armor operation were substantial, despite mechanical assistance, as the increased combat effectiveness came with correspondingly increased operational responsibilities. The deployment of T-45 armor to Alaskan front lines marked the beginning of a new era in military conflict, as American forces equipped with powered armor began systematically reversing territorial losses that had seemed permanent just months earlier. Chinese forces that had grown accustomed to technological superiority suddenly found themselves facing opponents who could absorb their best attacks while delivering devastating counterfire from weapons systems that conventional infantry could never have operated effectively. The Battle of Anchorage became the defining engagement for T-45 combat effectiveness, as American-powered infantry advanced through defensive positions that had been considered impregnable by conventional assault forces. The sight of American soldiers walking through artillery barrages while carrying heavy weapons had profound psychological impact on Chinese defenders who had never faced opponents with such capabilities. The armor's protection allowed aggressive tactics that would have been suicidal for conventional forces. Combat reports from Anchorage documented T-45 performance under the most demanding battlefield conditions. revealing both the platform's revolutionary capabilities and its operational limitations. The armor performed exceptionally well against small arms fire and fragmentation weapons, allowing soldiers to advance across open ground that would have been impassable for conventional forces. Energy weapons proved more problematic, as the armor's energy resistance was significantly lower than its kinetic protection. The logistical challenges of supporting T-45 operations in remote theaters like Alaska were immense, as the armor required specialized maintenance facilities, trained technicians, and constant supplies of fusion cores that were difficult to transport and expensive to manufacture. Each suit represented an investment equivalent to several conventional military vehicles, making the loss of powered armor units significant, not just tactically but economically. The complexity of the systems meant that field repairs were often impossible without proper facilities. The success of T-45 armor in reversing American military fortunes led to rapid expansion of production and deployment, with powered infantry units being formed throughout the American military establishment. The psychological boost provided by power armor extended beyond its tactical advantages to encompass broader morale improvements as American forces regained confidence in their ability to compete with technologically advanced opponents. The armor became a symbol of American technological superiority and military resurgence. But the rapid deployment of T-45 armor revealed systemic problems that had been overlooked in the urgency to field functional powered combat systems. The servo motors, while sophisticated for their time, were prone to mechanical failures under extended combat stress that left soldiers trapped in immobilized armor. The fusion power systems had reliability issues that could leave units without power at critical moments. Most significantly, the armor's energy weapon resistance proved inadequate against advanced Chinese laser and plasma systems. The maintenance requirements for T-45 armor were extensive and required specialized knowledge that was in short supply throughout the military establishment. Each suit needed daily inspections of servo systems, hydraulic pressure checks, power system diagnostics, and armor integrity assessments that took hours to complete properly. Units operating in combat conditions often had to choose between thorough maintenance and operational readiness, leading to preventable system failures that cost lives. The weight of T-45 armor, while manageable with servo assistance, created new categories of combat injuries as soldiers learned to operate with altered balance and momentum characteristics. The armor's protection encouraged aggressive tactics that sometimes exceeded the limits of what the servo systems could support, leading to mechanical failures during critical moments. Training programs evolved to address these issues, but the learning curve was steep and sometimes fatal. Field modifications to T-45 armor became common as units adapted the platform to specific operational requirements and environmental conditions. Arctic units developed heating modifications that improved cold weather performance. Urban combat specialists added close-quarters modifications that enhanced maneuverability in confined spaces. These field modifications often improved tactical performance but sometimes compromised the armor's reliability or safety margins. The production challenges associated with T-45 manufacturing revealed the limitations of American industrial capacity when faced with demands for precision components at unprecedented scales. The servo motors required manufacturing techniques that existed at only a few facilities nationwide, creating bottlenecks that limited production rates. Quality control became increasingly difficult as production quotas were elevated to meet military demand, leading to reliability issues in later production runs. The psychological impact of T-45 deployment extended beyond American forces to encompass Chinese military planning and civilian populations, who suddenly faced opponents with dramatically enhanced capabilities. Chinese propaganda efforts struggled to maintain morale in the face of reports about American soldiers who could walk through defensive fire while carrying weapons that could destroy fortified positions. The armor became a symbol of American military might that influenced diplomatic as well as military considerations. Training facilities for T-45 operation were established throughout the continental United States, creating new categories of military specialization and technical expertise. The soldiers selected for power armor training were typically among the most physically and mentally capable available, as the demands of operating sophisticated powered systems under combat stress required exceptional individuals. The training programs combined physical conditioning with technical education that approached engineering levels of complexity. The intelligence information gathered about Chinese responses to T-45 deployment revealed enemy efforts to develop countermeasures and competing technologies that could neutralize American-powered armor advantages. Chinese research into enhanced energy weapons was accelerated specifically to address the threat posed by American power armor, leading to a technological arms race that would continue until the Great War ended all such competitions permanently. The integration of T-45 armor into existing military doctrine required fundamental changes in tactical planning, logistics support, and command structures that had been developed for conventional forces. Powered infantry units operated with different capabilities and limitations than regular soldiers, requiring new approaches to battlefield coordination and strategic planning. The armor's effectiveness depended heavily on proper tactical employment, rather than simply fielding individual powered soldiers. The medical challenges associated with T-45 operation included unique categories of injuries related to servo system failures, hydraulic system ruptures, and power system malfunctions that military medical personnel had never previously encountered. Training programs for combat medics were expanded to include procedures for treating casualties trapped in damaged power armor. Specialized extraction tools were developed for removing injured soldiers from immobilized suits. The economic impact of T-45 production and deployment was substantial, representing one of the largest military procurement programs in American history. The costs associated with research, development, manufacturing, and operational support consumed significant portions of defense budgets that were already strained by the ongoing resource wars. The program's success justified these expenditures, but the financial commitment was enormous and unprecedented. The cultural significance of T-45 power armor extended beyond military applications to encompass broader American identity and technological confidence during the final decades before the Great War. The armor became a symbol of American ingenuity and determination, featured prominently in propaganda materials and public relations campaigns designed to maintain civilian morale during difficult wartime conditions. The image of American soldiers in power armor became iconic of late pre-war military might. As we reflect on the T-45's role in military history, we see a technology that bridged the gap between conventional warfare and the powered combat systems that would define military conflict until the bombs fell. It was humanity's first successful attempt to enhance individual soldiers with sophisticated mechanical systems, transforming ordinary people into powered warriors capable of extraordinary feats. The armor represented both the pinnacle of human engineering achievement and the desperate measures required when conventional approaches proved inadequate against evolving threats. The legacy of T-45 power armor would endure long after the Great War ended the conflicts for which it was designed, as post-war survivors discovered caches of the armor throughout the wasteland and learned to maintain and operate systems that represented the technological sophistication of a lost civilization. The Brotherhood of Steel would venerate these suits as relics of humanity's greatest achievements, while individual wastelanders would struggle to keep ancient servo motors functioning with improvised repairs and scavenged components. In the quiet moments of our exploration, let the T-45 remind us that human ingenuity, when faced with existential threats, can produce innovations that transcend the limitations of previous technological paradigms. These suits were born from necessity, but perfected through determination, representing the first step in humanity's journey toward powered augmentation that would define military capability until the very end of the old world. The excavator power armor stands as testament to humanity's capacity to envision technology beyond the narrow confines of warfare, representing a philosophical departure from the militaristic applications that had dominated powered armor development throughout the resource wars. While generals and weapons designers focused their efforts on creating more effective killing machines, a small team of engineers at West Tech Corporation pursued a radically different vision: powered armor, designed not to destroy, but to build, to extract, to sustain the industrial foundation upon which civilization itself depended. Harold Frost, the lead engineer responsible for excavator development, approached the challenge of civilian power armor with the methodical precision of someone who understood that the real battles of the 21st century would be fought not on foreign battlefields, but in the mines, factories, and construction sites where America's resource needs would ultimately be met or left wanting. His vision transcended the immediate military applications that had driven T-45 development, recognizing that powered armor technology possessed transformative potential for civilian industry that had barely been explored. The engineering philosophy behind excavator armor represented a fundamental shift from the combat-oriented design parameters that had shaped military power armor development. Where T-45 armor prioritized protection against enemy fire and enhanced combat effectiveness, excavator was designed around the specific requirements of industrial labor in environments that were hostile to human life but essential for resource extraction. The armor needed to protect workers from cave-ins, toxic gases, extreme temperatures, and the constant physical stress of heavy manual labor performed in confined spaces. The development timeline for excavator armor coincided with the escalating resource shortages that were driving international tensions toward the conflicts that would eventually consume the world. American mining operations were being pushed into increasingly dangerous and remote locations, as easily accessible deposits were exhausted and global competition for remaining resources intensified. Traditional mining equipment and safety procedures were proving inadequate for the extreme conditions required to maintain resource extraction rates that could support the American economy and war effort. The technical specifications of excavator armor reflected design priorities that differed dramatically from military applications, emphasizing durability, reliability, and specialized functionality over raw protective capability and combat effectiveness. The servo systems were calibrated for sustained heavy lifting rather than rapid combat movements, capable of operating continuously for extended shifts without the mechanical stress failures that plagued military armor under combat conditions. The hydraulic systems were designed for precision manipulation of mining equipment rather than weapon handling. The armor plating used in excavator construction prioritized protection against industrial hazards rather than enemy fire, featuring reinforced sections around areas most vulnerable to falling debris, chemical exposure, and mechanical impact from mining equipment. The helmet incorporated advanced sensor arrays designed to detect dangerous gas concentrations, structural instabilities, and ore deposits, rather than enemy movements and targeting solutions. The environmental systems were optimized for operation in confined underground spaces with limited air circulation. The power distribution system in excavator armor was engineered for efficiency and extended operation rather than peak performance, recognizing that mining operations required consistent power output over entire work shifts rather than short bursts of maximum capability. The fusion core consumption rate was optimized to support 12 to 16-hour operational periods, reflecting the demanding schedules of industrial mining operations. The power management systems included automated conservation protocols that reduced energy consumption during periods of reduced activity. The servo motor configurations in excavator armor were specifically designed for the repetitive motions and sustained loading conditions, characteristic of mining work, featuring enhanced torque output at lower speeds that enabled operators to manipulate heavy mining equipment with precision and control. The mechanical advantage provided by the servo systems allowed individual workers to operate drilling equipment, carry ore loads, and perform excavation tasks that would normally require multiple unaugmented workers or heavy machinery. The integration of specialized mining equipment directly into excavator armor represented innovative engineering that blurred the lines between personal protective equipment and industrial machinery. The suits could mount drilling attachments, ore analysis sensors, excavation tools, and material handling equipment that transformed the wearer into a self-contained mining operation capable of working in areas too confined or dangerous for conventional equipment. The modular attachment system allowed rapid reconfiguration for different mining tasks and conditions. The environmental protection systems in excavator armor were more sophisticated than military variants in specific areas related to industrial hazards, featuring advanced filtration for toxic mining gases, radiation shielding for operation near radioactive ore deposit, and thermal regulation for work in extreme temperature conditions. The suits provided complete atmospheric isolation with backup life support systems designed to sustain workers through equipment failures or emergency situations that might trap them underground for extended periods. The development of excavator armor revealed the broader potential for powered armor technology beyond military applications, demonstrating that the same engineering principles that enhanced combat effectiveness could be applied to civilian pursuits that were essential for maintaining industrial civilization. The success of the mining application sparked interest in other civilian uses, including construction, disaster relief, and hazardous material handling, though the Great War would end most civilian development programs before they could reach fruition. The training requirements for excavator operation were substantially different from military power armor programs, emphasizing safety protocols, industrial procedures, and equipment maintenance rather than combat tactics and weapons handling. Operators needed to understand mining, engineering, geology, and industrial safety, in addition to the technical aspects of power armor operation. The training programs combined traditional mining education with powered equipment operation, creating a new category of industrial specialist. The economic impact of excavator armor deployment in American mining operations was significant, enabling extraction from deposits that had previously been considered uneconomical due to safety concerns or technical difficulties. The enhanced productivity provided by powered workers allowed mining companies to maintain extraction rates despite increasingly challenging geological conditions. The armor's ability to operate in hazardous environments reduced casualty rates and insurance costs while improving overall operational efficiency. The psychological adaptation required for excavator operation differed from military power armor in that operators needed to overcome claustrophobia and industrial anxiety rather than combat stress, learning to trust mechanical systems while working in confined underground spaces where equipment failure could be fatal. The isolation experienced by excavator operators was different from combat isolation, characterized by the solitude of underground work rather than the hypervigilance of battlefield conditions. The maintenance requirements for excavator armor were extensive but predictable, as the suits operated in harsh but consistent environments that created wear patterns different from combat damage. The constant exposure to dust, moisture, and chemical contamination required daily cleaning and inspection procedures, while the sustained loading conditions necessitated regular replacement of servo components and hydraulic seals. Mining operations typically included dedicated maintenance facilities staffed by specialized technicians. The safety protocols associated with excavator operation were comprehensive and strictly enforced, recognizing that mechanical failure in mining environments could trap workers underground or expose them to toxic conditions. Emergency procedures included protocols for suit failure, power loss, structural collapse, and toxic gas exposure. Each operator carried emergency supplies and communication equipment designed to sustain them through rescue operations if mechanical systems failed. The productivity gains achieved through excavator deployment were substantial, with powered workers capable of extraction rates that exceeded conventional mining by factors that justified the significant capital investment required for armor procurement and maintenance. Individual operators could perform tasks that previously required teams of workers, while accessing areas that were too dangerous or confined for conventional mining techniques. The enhanced precision provided by servo-assisted control reduced waste and improved ore recovery rates. The environmental monitoring capabilities built into excavator armor provided valuable geological and safety data that improved overall mining operations beyond the direct productivity benefits of powered workers. The sensors could detect structural weaknesses, gas accumulations, ore deposits, and other conditions that affected mining planning and safety procedures. This data collection capability made excavator operations valuable for exploration and assessment activities in addition to extraction work. The modular design philosophy of excavator armor enabled customization for different mining conditions and operational requirements, with specialized configurations for coal mining, metal extraction, uranium mining, and other specific applications. Each configuration incorporated equipment and safety systems appropriate for particular hazards and working conditions. The adaptability of the platform made it suitable for diverse mining operations throughout the American industrial sector. The social impact of excavator deployment included changes in mining community dynamics, as powered workers became elite specialists within mining operations, earning higher wages and requiring advanced training that distinguished them from conventional miners. The technology created new career paths and educational requirements while potentially displacing traditional mining jobs, leading to social tensions in some mining communities. Labor unions had to adapt their organizations and bargaining strategies to accommodate powered workers. The international implications of American excavator technology were significant, as the enhanced mining capabilities provided strategic advantages in resource extraction that could influence global commodity markets and international relations. Other nations attempted to develop competing technologies or acquire American excavator suits through espionage and trade arrangements. The technology became part of broader economic and military competition between major powers. The research applications of excavator armor extended beyond immediate mining uses to include geological survey work, archaeological excavation, and scientific research in hazardous environments. The suits enabled human operators to work in conditions that would otherwise require expensive robotic systems or remain inaccessible entirely. Scientific institutions adapted excavator technology for specialized research applications that contributed to geological and environmental understanding. The post-war rediscovery of excavator armor by wasteland survivors represented a ironic reversal of its original peaceful purpose, as the suits designed for construction and extraction were often used for scavenging and warfare in the harsh realities of post-apocalyptic survival. However, some communities recognized the armor's original utility and used it for rebuilding efforts, mining operations, and construction projects that helped restore civilization to devastated areas. The preservation of excavator technology by groups like the Brotherhood of Steel reflected recognition that civilian applications of advanced technology were as valuable as military systems for long-term survival and recovery. The suits represented knowledge and capabilities that could support community development and resource extraction essential for sustainable settlements. The armor became symbols of productive labor rather than destructive warfare. The maintenance challenges faced by post-war excavator operators were severe, as the specialized components required for mining applications were often more difficult to scavenge or manufacture than military equivalents. The precision sensors and specialized attachments required technical expertise and replacement parts that were rarely available in wasteland conditions. Many post-war operators had to modify their suits extensively or operate with degraded functionality. The community impact of functional excavator armor in post-war settlements was substantial, as a single powered worker could accomplish construction and extraction tasks that would otherwise require large teams of manual laborers. The suits enabled small communities to undertake ambitious building projects and resource extraction efforts that would have been impossible with conventional post-war technology. The armor became foundations for economic recovery and growth. The educational legacy of excavator technology included the preservation of industrial knowledge and engineering principles that might otherwise have been lost in the post-war collapse. Operators and maintenance technicians preserved understanding of advanced manufacturing, precision engineering, and industrial safety that became valuable resources for rebuilding efforts. The technology served as a bridge between pre-war industrial capability and post-war recovery efforts. The philosophical implications of excavator armor extend beyond its technical capabilities to encompass broader questions about technology's role in human society and the choices societies make about how to apply scientific advancement. The armor represented a path not taken, a vision of technology serving constructive rather than destructive purposes, building rather than destroying, sustaining rather than consuming. In a world that had chosen warfare over cooperation, excavator armor stood as testament to alternative possibilities. As we consider the legacy of Harold Frost's vision, we see technology that embodied hope for humanity's productive potential rather than its capacity for destruction. The excavator suits remind us that the same engineering brilliance that created weapons of war could be directed toward tools of peace, that human creativity could serve life rather than death, construction rather than destruction. In the quiet depths of abandoned mines, these suits wait as monuments to the road not taken, the peaceful path that might have led away from the conflicts that consumed the world. The story of excavator armor teaches us that true strength sometimes lies not in the ability to destroy enemies, but in the capacity to build foundations, to extract resources, to sustain the productive efforts that make civilization possible. In a world that had forgotten the difference between strength and violence, these suits represented a gentler power that sought to nurture rather than dominate, to create rather than consume. The T-51 power armor represents the culmination of American engineering ambition during humanity's final decades, a technological masterpiece that emerged from the crucible of global warfare to become the defining symbol of pre-war military supremacy. Born from the harsh lessons learned during the early deployment of T-45 armor, the T-51 program embodied everything that American industry and scientific research could accomplish when unlimited resources met existential necessity in the face of enemies who threatened not just territorial integrity, but the very survival of the American way of life. The genesis of T-51 development began in the aftermath of initial combat reports from Alaska, where T-45 armor had proven revolutionary but imperfect, demonstrating both the immense potential of powered infantry and the critical limitations that prevented American forces from achieving the decisive victories that military leadership demanded. The energy weapon vulnerability that plagued T-45 operations became a strategic concern when Chinese forces began deploying advanced laser and plasma systems specifically designed to counter American power armor. Advantages. The materials science revolution that enabled T-51 construction represented perhaps the greatest leap forward in protective technology since the development of steel armor, requiring breakthroughs in polymer chemistry, composite manufacturing, and metallurgical engineering that pushed the boundaries of what 21st century industrial capability could achieve. The polylaminate composite that formed the armor's primary protection was a masterwork of engineered materials, combining multiple layers of specialized polymers with metallic reinforcement in configurations that had been impossible to manufacture just years earlier. The reflective properties engineered into T-51 armor plating addressed the energy weapon vulnerabilities that had proven so costly during early power armor deployments, incorporating surface treatments and composite structures that could disperse laser energy across wide areas rather than allowing focused beams to burn through protective layers. The armor's ability to reflect and scatter energy weapons fire represented a fundamental shift in defensive philosophy, moving beyond simple absorption to active countermeasures that turned enemy weapons against themselves. The titanium alloy matrix that provided T-51's structural foundation was lighter and stronger than anything previously used in power armor construction, enabling enhanced protection without the weight penalties that had limited T-45 mobility and endurance. The alloy's composition was classified at the highest levels of military secrecy, incorporating rare earth elements and precision manufacturing techniques that required dedicated production facilities operated under conditions of extreme security and quality control. The servo motor systems integrated into T-51 armor represented refinements of the hydraulic technology that had been pioneered in earlier power armor platforms, featuring improved response times, enhanced precision, and reliability characteristics that addressed the mechanical failures that had plagued T-45 operations under extended combat stress. The servo systems were designed for sustained operation under the most demanding battlefield conditions, with redundant backup systems and fail-safe mechanisms that prevented catastrophic failures. The power distribution architecture of T-51 armor incorporated lessons learned from extensive T-45 field operations, featuring improved fusion core efficiency and power management systems that extended operational duration while supporting the enhanced capabilities that made the armor superior to its predecessors. The fusion technology had been refined through years of combat experience, addressing reliability issues and power consumption problems that had limited earlier power armor effectiveness. The heads-up display systems integrated into T-51 helmets represented the pinnacle of pre-war battlefield information technology, providing soldiers with tactical data, target identification, ammunition status, and environmental information through interface systems that seemed almost magical in their sophistication and ease of use. The display technology incorporated advances in miniaturization and processing power that enabled real-time battlefield analysis and decision support that enhanced soldier effectiveness beyond simple physical augmentation. The environmental protection systems built into T-51 armor were more comprehensive than any previous military equipment, providing complete protection against chemical weapons, biological agents, radioactive contamination, and extreme environmental conditions that might be encountered on battlefields, ranging from Arctic wastes to tropical jungles. The life support systems included atmospheric recycling, temperature regulation, and emergency backup systems that could sustain soldiers through equipment failures or extended isolation. The deployment of T-51 armor to the Anchorage front transformed what had been a grinding war of attrition into a decisive American victory that demonstrated the revolutionary potential of properly executed power armor technology. American soldiers wearing T-51 suits advanced through Chinese defensive positions that had been considered impregnable. Their enhanced protection and firepower overwhelming enemy forces that had grown accustomed to technological parity with American equipment. The Battle of Anchorage became the defining engagement that proved T-51 armor's superiority over all competing technologies, as American-powered infantry systematically dismantled Chinese defensive networks while sustaining casualties that were negligible compared to conventional assault operations. The sight of American soldiers walking through energy weapon fire while delivering devastating return attacks broke Chinese morale and tactical doctrine simultaneously, forcing enemy commanders to abandon positions they had fortified for months. The psychological impact of T-51 deployment extended far beyond immediate battlefield effects to encompass broader strategic implications for global military balance. As other nations realized that American power armor technology had achieved levels of sophistication that could not be matched through conventional research and development programs, the armor became a symbol of American technological supremacy that influenced diplomatic negotiations and strategic planning throughout the international community. The Chinese response to T-51 deployment revealed the desperation of a nation facing technological obsolescence on the battlefield, as enemy research programs were accelerated beyond safe parameters in attempts to develop countermeasures or competing systems that could restore tactical balance. Chinese efforts to capture intact T-51 suits led to increasingly desperate military operations that revealed the strategic importance that enemy leadership placed on understanding American power armor technology. The intelligence gathered from captured Chinese equipment and documents revealed extensive efforts to reverse engineer American power armor technology, including industrial espionage operations, scientific recruitment programs, and research initiatives that consumed significant portions of Chinese military resources. The inability of Chinese scientists and engineers to replicate T-51 capabilities, despite access to captured equipment, demonstrated the sophisticated manufacturing and materials science knowledge required for successful power armor development. The production challenges associated with T-51 manufacturing pushed American industrial capacity to its absolute limits, requiring the construction of specialized facilities, the development of new manufacturing techniques, and the training of workers in precision assembly procedures that had never been attempted at scale. The quality control requirements for T-51 components exceeded automotive industry standards, demanding precision and consistency that tested the capabilities of even the most advanced American manufacturing systems. The logistical support systems required for T-51 operations were extensive and complex, encompassing specialized maintenance facilities, trained technician programs, supply chains for rare components, and transportation networks capable of supporting power armor operations in remote theaters. Each T-51 suit required support infrastructure equivalent to multiple conventional military vehicles, making power armor deployment a strategic decision that involved significant resource allocation and planning considerations. The training programs developed for T-51 operators represented the most comprehensive military education systems ever created, combining physical conditioning, technical training, tactical instruction, and psychological preparation in programs that transformed selected soldiers into elite-powered infantry specialists. The selection criteria for T-51 training were extraordinarily demanding, as the cognitive and physical requirements for effective power armor operation exceeded the capabilities of most military personnel. The tactical doctrine that evolved around T-51 deployment revolutionized American military strategy, enabling operational approaches that had been impossible with conventional forces, while creating new categories of strategic objectives and battlefield goals. Power armor units could accomplish missions that would have required entire battalions of conventional soldiers, while sustaining casualties that were minimal compared to traditional assault operations. The maintenance requirements for T-51 armor were sophisticated but manageable with proper facilities and trained personnel, as the improved reliability of the platform reduced the constant mechanical problems that had plagued T-45 operations. The armor's modular design enabled field replacement of damaged components, while the improved materials and construction techniques reduced wear and tear under normal operational conditions. The international ramifications of T-51's success included shifts in global military balance that influenced alliance structures, trade relationships, and diplomatic negotiations throughout the world. Nations that had been neutral in the resource wars began aligning themselves with American interests as the implications of power, armor, superiority became apparent. The armor represented not just tactical advantage but strategic dominance that could determine the outcomes of international conflicts. The technological spin-offs from T-51 development influenced civilian applications and research programs throughout American industry, as the advanced materials, manufacturing techniques, and engineering knowledge developed for power armor found applications in construction, transportation, and consumer products. The armor program drove innovations that extended far beyond military applications to encompass broader technological advancement. The psychological effects of wearing T-51 armor on American soldiers were generally positive, as the enhanced protection and capability provided confidence and morale improvements that translated into better battlefield performance. However, some soldiers experienced adjustment difficulties related to the increased responsibility and capability that came with power armor operation, requiring psychological support and counseling services that were integrated into training programs. The intelligence value of T-51 technology was enormous, as the armor incorporated advances in multiple scientific disciplines that provided insights into enemy capabilities, battlefield conditions, and tactical requirements that informed broader military planning and strategic decision-making. The data collected by power armor sensors contributed to understanding of combat environments and enemy systems that enhanced American military effectiveness beyond the direct combat contributions of powered infantry. The cultural impact of T-51 armor extended throughout American society, as the suits became symbols of national technological achievement and military prowess that were featured prominently in propaganda materials, public relations campaigns, and civilian morale efforts. The armor represented everything that was best about American engineering and military capability, embodying national pride and confidence in ways that influenced public support for military operations and resource allocation. The Brotherhood of Steel's veneration of T-51 armor as the pinnacle of pre-war achievement reflects the suit's status as perhaps the most successful integration of advanced technology and military application ever accomplished, representing a standard of excellence that has never been exceeded Despite centuries of post-war technological development, the armor embodies the engineering principles and manufacturing capability that the Brotherhood seeks to preserve and restore. The post-war discovery of T-51 suits throughout the wasteland has provided survivors with access to technology that represents the absolute peak of pre-war military engineering, though the maintenance and operational challenges of keeping such sophisticated systems functional in post-apocalyptic conditions have proven enormous. The suits require levels of technical knowledge and replacement parts that are extremely difficult to obtain in wasteland conditions. The legendary status of T-51 armor among wasteland survivors reflects not just its practical capabilities, but its symbolic importance as a reminder of what human civilization was capable of achieving when resources and knowledge were applied to constructive purposes. The armor represents hope that such achievements might someday be possible again, that the technological capabilities of the old world were not permanently lost but merely temporarily inaccessible. The preservation efforts undertaken by various wasteland factions to maintain functional T-51 suits demonstrate the armor's continued relevance and importance despite the changed conditions of post-war survival. These efforts represent significant resource investments and technical challenges that communities undertake because they recognize the strategic and symbolic value that functional power armor represents in the ongoing struggle to rebuild civilization. The engineering legacy of T-51 development continues to influence post-war technology development as survivors attempt to understand and replicate the advanced systems that made the armor so effective. The suits serve as laboratories and educational tools for post-war engineers and technicians who are working to restore technological capabilities that were lost in the nuclear exchange. As we reflect on the achievement that T-51 armor represents, we see technology that embodied the highest aspirations of human engineering and military science, created through the application of unlimited resources and brilliant minds to the challenge of protecting soldiers while enabling them to accomplish missions that had previously been impossible. The armor stands as testament to what human civilization could accomplish when necessity met capability in the crucible of existential conflict. In the quiet moments of contemplation, let T-51 remind us that human achievement, when properly directed and adequately supported, can produce innovations that transcend the limitations of previous technological paradigms. These suits were more than military equipment. They were expressions of human potential, realized through scientific method, engineering excellence, and manufacturing precision that represented the pinnacle of pre-war civilization's technological capability. The legacy of T-51 armor extends beyond its practical military applications to encompass broader lessons about the relationship between technology and human society, demonstrating that sophisticated engineering, when properly applied, can enhance rather than diminish human capability. The armor represented partnership between human intelligence and mechanical precision that multiplied rather than replaced human potential, creating capabilities that neither could achieve independently. The T-60 power armor stands as perhaps the most controversial piece of military hardware in pre-war American history, a technological achievement so shrouded in temporal mystery and political intrigue that its very existence challenges our understanding of the final months before the Great War consumed civilization in nuclear fire. Introduced without fanfare or official announcement in the chaotic final year of 2077, T-60 armor appeared in American military inventories with such sudden ubiquity that its development timeline raises questions that have never been satisfactorily answered by surviving military records or corporate documentation. The mysterious circumstances surrounding T-60 development, begin with the complete absence of any mention of the armor in military procurement documents, research and development reports, or industrial planning materials from the years preceding its deployment. Unlike T-45 and T-51 armor programs, which generated extensive documentation covering every aspect of design, testing, and production, T-60 armor seems to have materialized from classified programs so secret that even the usual paper trails of military bureaucracy were eliminated or never created in the first place. The timeline problems associated with T-60 armor become even more perplexing when examined against the backdrop of known American military operations and strategic priorities during the final year before the nuclear exchange. With T-51 armor having proven decisively effective in the Anchorage campaign, and Chinese resistance having collapsed under the pressure of American-powered infantry, the military rationale for developing an entirely new power armor platform during 2077 remains unclear and potentially suspicious. Corporate records from the period show Westech Corporation and other defense contractors were fully committed to T-51 production, and various experimental projects related to advanced power armor variants, with no evidence of the massive research and development programs that would have been necessary to create T-60 armor's sophisticated improvements over existing technology. The industrial capacity required to develop and manufacture an entirely new power armor platform would have required years of preparation and resource allocation that should have left extensive documentary evidence. The technical specifications of T-60 armor reveal design philosophies and engineering approaches that differ substantially from the progressive development patterns that had characterized American power armor evolution from T-45 through T-51 platforms. Rather than representing incremental improvements in materials science and servo technology, T-60 armor incorporated design changes that suggested access to manufacturing techniques and materials that had not been available during earlier power armor development programs. The armor plating used in T-60 construction was significantly thicker and heavier than T-51 materials, prioritizing maximum protection over the mobility considerations that had influenced earlier power armor design decisions. The composite construction incorporated metallic elements and polymer matrices that were more sophisticated than anything used in previous American military applications, suggesting either breakthrough discoveries in materials science or access to previously unknown manufacturing capabilities. The servo motor systems integrated into T-60 armor provided enhanced strength augmentation compared to T-51 platforms, featuring more powerful hydraulic systems and improved response characteristics that enabled soldiers to operate heavier weapons and carry larger equipment loads. The mechanical advantages provided by T-60 servos exceeded the capabilities of earlier power armor by margins that suggested fundamental improvements in hydraulic engineering and precision manufacturing, rather than incremental refinement. The power distribution architecture of T-60 armor incorporated fusion technology that was more efficient than previous power armor platforms while supporting the enhanced systems and heavier construction that characterized the power design. The fusion cores required for T-60 operation were identical to those used in earlier armor, but the power management systems achieved better performance through engineering improvements that are not fully understood from surviving technical documentation. The heads-up display systems built into T-60 helmets featured enhanced targeting computers, improved sensor integration, and communication systems that exceeded the capabilities of T-51 armor in ways that suggested access to miniaturization and processing technologies that had not been available during earlier development programs. The sophistication of T-60 electronics implied advances in semiconductor technology and computer science that were not reflected in other American military systems of the period. The environmental protection systems incorporated into T-60 armor were more comprehensive than earlier platforms, featuring enhanced filtration systems, improved thermal regulation, and radiation shielding that suggested the armor was designed for operating environments that were more hazardous than typical battlefield conditions. The emphasis on radiation protection was particularly notable, given that nuclear weapons had not yet been deployed and radioactive battlefield conditions were not considered primary design requirements for military equipment. The deployment patterns of T-60 armor during its brief operational period raise additional questions about the armor's intended purpose and the strategic thinking behind its rapid production and distribution. Rather than being deployed to frontline combat units fighting Chinese forces or other external enemies, T-60 armor was primarily issued to National Guard units and domestic security forces responsible for maintaining civil order within the continental United States. The domestic deployment emphasis suggests that T-60 armor was developed specifically for operations against American civilian populations, rather than foreign military forces, representing a shift in power armor doctrine from external warfare to internal security and population control. The armor's enhanced protection and intimidating appearance made it ideal for riot control and civil disturbance operations, where psychological impact was as important as physical capability. The timing of T-60 deployment coincided with escalating civil unrest throughout the United States as resource shortages, economic disruption, and military casualties from the resource wars created social tensions that threatened domestic stability. Food riots, labor strikes, and anti-war demonstrations were becoming increasingly violent and widespread, requiring military intervention on scales that strained the capabilities of conventional security forces. Military records from the period document the deployment of T-60 equipped units to suppress civilian disturbances in major American cities, where the armor's psychological impact proved as effective as its protective capabilities in controlling crowds and deterring resistance to government authority. The sight of American soldiers in advanced power armor confronting American civilians created images that captured the growing militarization of domestic policy during the final months before the war. The manufacturing capacity required to produce T-60 armor in the quantities that appeared in military inventories during 2077 would have required industrial infrastructure and resource allocation on scales that should have been visible in economic and industrial planning documents. The absence of such documentation suggests either that T-60 production was conducted through channels that bypassed normal procurement procedures, or that records of the program were systematically destroyed or classified beyond normal military security levels. The quality control and testing procedures that would have been necessary to validate T-60 armor for military service would typically have required months or years of evaluation under various operational conditions. The rapid deployment of the armor, without apparent testing phases, suggests either that safety and performance standards were waived due to urgent operational requirements, or that testing was conducted through classified programs that left no accessible records. The training programs required to prepare soldiers for T-60 operation appear to have been conducted through existing power armor training facilities using modified T-51 curricula, suggesting that the armor was designed to be operated by soldiers with existing power armor experience rather than requiring specialized training programs. This design decision would have accelerated deployment schedules, but may have limited the armor's effectiveness in applications that differed significantly from conventional power armor missions. The maintenance and logistics support systems established for T-60 armor utilized existing power armor infrastructure, with modifications to accommodate the platform's enhanced systems and different component Specifications. The compatibility with existing support systems was probably intentional to enable rapid deployment without requiring extensive new infrastructure development, but created maintenance challenges when T-60 specific components were not available through normal supply channels. The psychological impact of T-60 armor on American military personnel who were required to use the equipment against civilian populations was significant and largely negative, as soldiers trained for combat against foreign enemies found themselves deployed in domestic security roles that challenged their understanding of military service and patriotic duty. Reports from the period document declining morale and increasing disciplinary problems among units equipped with T-60 armor. The civilian response to T-60 deployment was overwhelmingly negative, as the appearance of advanced military hardware in domestic law enforcement applications was perceived as evidence of government militarization and authoritarian tendencies that violated traditional American principles of civilian governance and military restraint. The armor became a symbol of government oppression that influenced public opinion and political opposition to military policies. The international implications of T-60 deployment were complex and contributed to escalating tensions that would ultimately lead to the nuclear exchange that ended the pre-war period. Foreign intelligence services interpreted American domestic deployment of advanced military equipment as evidence of internal instability that might create opportunities for exploitation, while also representing enhanced American military capabilities that could threaten international interests. The strategic doctrine that governed T-60 employment differed substantially from conventional power armor tactics, emphasizing crowd control, area denial, and psychological intimidation rather than direct combat engagement and enemy destruction. The armor's capabilities were optimized for operations against lightly armed or unarmed civilian populations rather than military targets, reflecting its specialized role in domestic security applications. The Brotherhood of Steel's post-war adoption of T-60 armor as their standard platform reflects both the suit's superior technical capabilities and its symbolic importance as the most advanced power armor platform that was mass-produced before the Great War ended. Technological development. The Brotherhood's reverence for T-60 armor represents their commitment to preserving the highest achievements of pre-war American military technology. The post-war discovery of T-60 armor throughout the wasteland in quantities that exceeded other power armor platforms demonstrates the extensive production and distribution that occurred during the armor's brief operational period. The widespread availability of T-60 suits provided post-war survivors with access to advanced protective technology, though the maintenance challenges of keeping such sophisticated systems operational in wasteland conditions proved significant. The modification potential of T-60 armor has made it popular among post-war factions and individual survivors who appreciate the platform's combination of protection, capability, and upgrade flexibility. The armor's robust construction and modular design enable extensive customization for different operational requirements, from combat applications to utility and construction work that supports community building efforts. The preservation efforts undertaken by various wasteland organizations to maintain T-60 armor reflect recognition of its value as both practical equipment and technological artifact that represents pre-war manufacturing capability. These preservation programs require significant resource investments, but are considered worthwhile due to the armor's continued effectiveness and symbolic importance. The mystery surrounding T-60 development continues to generate speculation and investigation among wasteland historians and technology specialists, who recognize that understanding the armor's origins might provide insights into the political and military dynamics that led to the Great War. The armor represents questions about pre-war American society that remain unanswered despite extensive study and analysis. The ethical implications of T-60 armor extend beyond its controversial origins to encompass broader questions about the relationship between technology and political power, the militarization of civilian governance, and the responsibility of engineers and manufacturers who create systems that may be used for purposes they never intended. The armor embodies technological capability divorced from moral consideration of its applications. The technical legacy of T-60 armor influences post-war power armor development as wasteland engineers and technicians study its systems to understand advanced manufacturing techniques and design principles that might be applied to new projects. The armor serves as an educational resource that preserves knowledge about sophisticated engineering and materials science that might otherwise be lost. The cultural impact of T-60 armor in post-war society reflects both admiration for its technological sophistication and unease about its original domestic security applications, creating complex reactions among survivors who appreciate its protective capabilities while recognizing its symbolic associations with pre-war authoritarianism. The armor represents the ambiguous legacy of pre-war American technological achievement. As we contemplate the enigma of T-60 armor, we encounter technology that challenges simple narratives about pre-war American society and the linear progression of military development during the resource wars. The armor represents mysteries that may never be fully resolved. Questions about the final months of the old world that died with the civilization that created them. In the armor's sophisticated systems and controversial origins, we see reflections of the complex political and social forces that drove humanity toward the nuclear precipice from which civilization never fully recovered. The T-60 stands as testament to both the heights of human engineering achievement and the depths of political paranoia that characterized the final years before the bombs fell, embodying the technological brilliance and moral blindness that defined the pre-war world's approach to power and protection. In its steel and circuitry, we find preserved the contradictions of a civilization that could create marvels of protective technology while simultaneously preparing to use that technology against its own citizens. The X-01 advanced power armor represents humanity's most ambitious attempt to transcend the limitations of conventional protective technology, born from experimental programs that pushed the boundaries of materials, science, and engineering philosophy beyond anything previously attempted in the desperate final years before nuclear fire consumed the world. Unlike the linear progression that had characterized American power armor development from T-45 through T-60 platforms, X-01 armor emerged from classified research programs that explored radical departures from established design principles, seeking to create protective systems that would redefine what individual soldiers could accomplish on future battlefields. The origins of X-01 development trace back to 2075, when American military planners began considering scenarios that extended beyond the immediate challenges of the resource wars to encompass longer-term strategic requirements for maintaining global dominance in an increasingly unstable world. The success of T-51 armor in conventional conflicts had demonstrated the revolutionary potential of powered infantry, but forward-thinking strategists recognized that future enemies might develop countermeasures that would neutralize existing power armor advantages. The experimental nature of X-01 research reflected military recognition that incremental improvements to existing power armor platforms might prove insufficient for maintaining American technological superiority against adversaries who were rapidly developing their own advanced military systems. The armor program represented a philosophical shift from refining proven technologies to exploring entirely new approaches that might create generational advantages rather than marginal improvements over existing capabilities. The classification levels surrounding X-01 development exceeded even the security measures that had protected previous power armor programs, with research conducted through compartmentalized projects that prevented most participants from understanding the full scope of their contributions to the overall program. The security protocols were so restrictive that complete technical documentation was fragmented across multiple facilities and research groups, creating vulnerabilities that would later complicate post-war reconstruction efforts. The materials science breakthroughs that enabled X-01 construction represented some of the most advanced engineering achievements of the pre-war period, incorporating ceramic composite technologies that had been theoretical concepts just years earlier. The armor's primary protective layers utilized polymer matrices that were lighter and stronger than metallic alternatives, while providing enhanced protection against both kinetic and energy weapons through sophisticated energy distribution mechanisms. The ceramic composite plating that formed X-01's defensive foundation was manufactured using precision techniques that required environmental conditions and quality control standards that exceeded anything previously attempted in military production. The composites incorporated microscopic structures that were engineered at molecular levels to optimize protective characteristics while minimizing weight penalties that had limited earlier power armor, mobility, and endurance. The polymer matrix systems integrated throughout X-01 armor provided impact distribution capabilities that were fundamentally different from the simple absorption mechanisms used in conventional armor plating. When struck by projectiles or energy weapons, the polymer systems would redistribute impact forces across wide areas of the armor's structure, preventing localized failures that could compromise overall protective integrity. The advanced servo motor systems incorporated into X-01 armor featured precision manufacturing and sophisticated control algorithms that provided enhanced strength augmentation while improving response characteristics compared to earlier power armor platforms. The servos utilized hydraulic systems that operated at higher pressures with improved efficiency, enabling greater mechanical advantage while reducing power consumption requirements. The fusion power systems developed for X-01 armor incorporated refinements to core technology that improved energy output while extending operational duration beyond what had been achieved in previous power armor applications. The power management systems featured automated optimization protocols that adjusted energy distribution based on operational requirements, maximizing efficiency while maintaining peak performance capabilities when necessary. The heads-up display technology integrated into X-01 helmets represented the cutting edge of battlefield information systems, incorporating processing capabilities and sensor integration that exceeded anything previously deployed in individual combat equipment. The displays provided real-time tactical analysis, threat assessment, and target identification through artificial intelligence systems that assisted soldiers in making split-second decisions during combat operations. The environmental protection systems built into X-01 armor were more comprehensive than any previous military equipment, providing complete isolation from chemical, biological, and radioactive threats while maintaining comfortable internal conditions through sophisticated life support systems. The filtration technology could process contaminated atmosphere through multiple purification stages that removed virtually any known threat to human health. The modular design philosophy that governed X-01 construction enabled extensive customization for different mission requirements and operational environments, with standardized attachment points and power distribution systems that supported specialized equipment configurations. The armor could be rapidly reconfigured for different roles, from assault operations to reconnaissance missions to technical support applications. The limited production of X-01 armor reflected both the experimental nature of the program and the extraordinary manufacturing requirements that made mass production impractical with available industrial capacity. Each suit required hand assembly by specially trained technicians using precision tools and techniques that could not be automated or scaled to conventional production levels. The testing protocols developed for X-01 evaluation were more comprehensive than previous power armor programs, incorporating simulated combat scenarios, environmental stress testing, and long-term durability assessments that revealed both the armor's exceptional capabilities and its operational limitations. The testing revealed performance characteristics that exceeded design specifications in most areas, while identifying potential vulnerabilities that might be exploited by sophisticated opponents. The deployment of X-01 armor was extremely limited, with prototype units allocated to elite special operations forces for field evaluation under actual combat conditions. The operational data gathered from these deployments provided valuable insights into the armor's performance, while revealing areas where further development was needed to achieve full operational capability. The nuclear exchange that ended the pre-war period occurred before X-01 development could progress beyond prototype stages, leaving the armor's full potential unrealized and its technological secrets scattered among destroyed research facilities and classified archives that were lost in the global catastrophe. The incomplete state of the program, when the bombs fell, created opportunities for post-war organizations to continue development using surviving research materials. The Enclave's acquisition of X-01 research data represents one of the most significant technological preservation efforts of the post-war period, as Enclave scientists and engineers salvaged prototype units, technical documentation, and manufacturing equipment from the ruins of classified facilities. The preservation of this knowledge enabled continued development of X-01 technology under post-war conditions that were dramatically different from its original research environment. The 2 centuries of development that the Enclave devoted to perfecting X-01 technology transformed the experimental prototypes into fully operational, advanced power armor that exceeded the performance of any pre-war system. The Enclave's improvements incorporated lessons learned from extensive combat experience, while pushing the original design concepts to their full potential through sustained research and development efforts. The advanced power armor that emerged from Enclave development programs retained the fundamental design philosophy of X-01, while incorporating improvements that addressed the limitations identified during pre-war testing. The armor featured enhanced protection, improved reliability, and expanded capability while maintaining the modularity and customization potential that had characterized the original design. The specialized variants of advanced power armor developed by the Enclave reflect the organization's commitment to maximizing the platform's potential for different operational requirements. Each variant was optimized for specific mission profiles, while maintaining commonality with the base design that simplified logistics and training requirements. The Hellfire Power Armor variant represents the Enclave's attempt to create specialized equipment for operations in extremely hazardous environments, featuring enhanced radiation shielding and thermal protection that enables soldiers to operate in conditions that would be instantly fatal to unprotected personnel. The armor's distinctive appearance and intimidating presence reflect its specialized role in high-threat operations. The Tesla power armor configuration incorporates advanced electrical systems that provide enhanced protection against energy weapons, while enabling offensive capabilities that turn the armor into a walking electrical weapon system. The Tesla coils integrated into the armor create defensive fields that can disable enemy equipment, while providing additional protection against electronic warfare attacks. The manufacturing challenges associated with post-war X-01 production were enormous, requiring the Enclave to develop new production techniques and quality control procedures that could maintain the precision requirements of the armor while working with limited industrial resources. The solutions developed by Enclave engineers represent remarkable achievements in post-apocalyptic manufacturing technology. The training requirements for X-01 operation exceed those of any other power armor platform, reflecting the sophisticated systems and advanced capabilities that require extensive education and practice to master effectively. Enclave training programs combine technical instruction with tactical education and psychological preparation that transforms selected personnel into elite-powered infantry specialists. The psychological impact of X-01 armor on both wearers and opponents is significant, as the armor's advanced capabilities and intimidating appearance create confidence in friendly forces while generating fear and uncertainty in enemy personnel. The armor has become a symbol of Enclave technological superiority that influences tactical and strategic considerations in post-war conflicts. The maintenance requirements for X-01 armor are extensive but manageable with proper facilities and trained personnel, though the sophisticated systems require diagnostic equipment and replacement parts that are difficult to obtain outside of Enclave facilities. The armor's modular design enables component replacement and upgrade installation that maintains operational capability over extended periods. The battlefield performance of X-01 armor has proven exceptional in the limited engagements where it has been deployed, with the armor's protection and capabilities enabling tactical approaches that would be impossible with conventional equipment. The armor's effectiveness against various threat types has validated the design concepts, while revealing areas where further improvement might be beneficial. The intelligence value of X-01 technology extends beyond its direct military applications to encompass the manufacturing techniques, materials science, and engineering knowledge that its construction requires. The armor represents preserved pre-war knowledge that might otherwise have been permanently lost, making it valuable for broader technological reconstruction efforts. The strategic implications of X-01 deployment by the Enclave have influenced post-war military planning and alliance considerations throughout the wasteland, as other factions recognize that advanced power armor represents capabilities that cannot be matched through conventional means. The armor has become a factor in diplomatic and strategic calculations that extend far beyond immediate tactical considerations. The post-war discovery of X-01 prototypes and research materials by various wasteland factions has created opportunities for technological development that might not otherwise have been possible, though the complexity of the systems has limited successful reconstruction efforts to organizations with substantial technical capabilities and resources. The preservation efforts undertaken to maintain functional X-01 armor reflect recognition of its value as both practical equipment and technological artifact that represents the pinnacle of pre-war American engineering achievement. These efforts require significant resource investments, but are considered essential for maintaining capabilities that might be crucial for long-term survival and recovery. The ethical implications of X-01 technology encompass questions about the concentration of advanced military capabilities in the hands of organizations that may not represent broader human interests, as well as concerns about the social and political effects of such dramatic technological advantages. The armor raises fundamental questions about power, responsibility, and the appropriate use of advanced technology in post-apocalyptic society. The research applications of X-01 technology extend beyond military uses to encompass scientific investigation, environmental monitoring, and exploration activities that require protection against extreme hazards. The Armour's advanced sensor systems and environmental protection capabilities make it valuable for understanding post-war conditions and planning recovery efforts. The cultural significance of X-01 armour in post-war society reflects both admiration for its technological sophistication and concerns about its concentration in the hands of organizations with questionable motivations and methods. The armor represents the complex legacy of pre-war American technology and the challenges of managing advanced capabilities in a world that lacks the institutional structures that originally controlled their development and deployment. As we reflect on the achievement that X-01 armor represents, we see technology that embodies both the highest aspirations and the deepest concerns about human technological development. The armor demonstrates what can be accomplished when unlimited resources meet brilliant minds in pursuit of protective excellence. Yet it also raises questions about the wisdom of creating capabilities that exceed our ability to control their consequences. In the quiet contemplation of X-01's legacy, we encounter the fundamental paradox of advanced technology, that our greatest achievements in protecting human life may also represent our greatest threats to human freedom and dignity. The armor stands as testament to human ingenuity, while serving as warning about the responsibilities that accompany technological power. The story of X-01 reminds us that technological advancement without moral consideration can create tools that serve purposes their creators never intended, that the same engineering brilliance that seeks to protect may also enable oppression. In the armor's sophisticated systems, we find reflected both humanity's potential for transcendence and its capacity for creating instruments of its own limitation. The ultrasight power armor emerges from the Brotherhood of Steel's relentless pursuit of technological superiority through the integration of extraterrestrial materials that challenge conventional understanding of metallurgy and protective engineering. Born from the discovery of ultrasight deposits in the Appalachian wasteland, this armor represents humanity's first successful attempt to harness alien technology for military applications, creating protective systems that transcend the limitations of terrestrial materials through the incorporation of crystalline structures that appear to violate known laws of physics and chemistry. The origins of ultrasight discovery trace back to the Brotherhood's systematic survey operations in the Appalachian region, where geological anomalies and unusual energy readings led expeditionary teams to deposits of crystalline material that exhibited properties unlike anything in pre-war scientific literature. The initial analysis of these deposits revealed molecular structures that seemed to incorporate elements not found on the periodic table, suggesting origins that extended beyond terrestrial chemistry into realms of materials science that human civilization had never encountered. The Brotherhood's decision to pursue ultrasight integration into power armor systems reflected their institutional commitment to preserving and advancing pre-war technology through whatever means became available, even when those means involved working with materials whose fundamental properties remained incompletely understood. The potential advantages offered by ultrasight incorporation were deemed worth the risks associated with experimental programs that pushed beyond the safety margins of conventional engineering practice. The extraction of ultrasight from its natural deposits required the development of specialized mining techniques and equipment, as conventional extraction methods proved inadequate for harvesting crystalline materials that existed in quantum states not normally encountered in terrestrial geology. The mining operations resembled archaeological excavations more than traditional resource extraction, with each specimen requiring careful handling and preservation to maintain its unique properties. The initial attempts at ultrasight integration into existing power armor platforms resulted in catastrophic failures that claimed several Brotherhood scientists and technicians, as the alien materials reacted unpredictably with conventional armor components and power systems. These early failures revealed that ultrasight incorporation required complete redesign of power, armor, architecture, rather than simple material substitution in existing designs. The research breakthrough that enabled successful ultrasight integration came through the discovery that the alien materials required specific electromagnetic field configurations to maintain stability when incorporated into complex technological systems. The Brotherhood's scientists developed containment protocols and field generation equipment that could maintain ultrasight in stable states while preserving its beneficial properties for armor applications. The crystalline matrix that forms the foundation of ultrasight power armor represents a fundamental departure from conventional armor construction, incorporating alien materials in configurations that create protective properties through quantum mechanical effects, rather than simple physical barriers. The ultrasight crystals exist in multiple dimensional states simultaneously, creating protective fields that can deflect energy weapons through mechanisms that remain incompletely understood despite extensive study. The energy weapon resistance provided by ultrasight integration exceeds anything achieved through conventional armor materials, as the crystalline structures appear to absorb, redirect, and sometimes reflect energy attacks through processes that violate conservation of energy principles as understood by pre-war physics. The armor can withstand sustained laser bombardment that would instantly vaporize conventional protective systems, making it invaluable against enemies equipped with advanced energy weapons. The power requirements for maintaining ultrasight stability within armor systems are substantial, requiring fusion cores that have been specially modified with electromagnetic field generators and quantum stabilization circuits. The power consumption associated with ultrasight armor operation exceeds that of conventional power armor platforms, but the enhanced protection justifies the increased energy demands for specialized applications. The manufacturing challenges associated with ultrasight power armor production are enormous, requiring precision techniques that exceed the capabilities of most post-war industrial facilities. Each piece of ultrasight must be individually shaped and incorporated into armor components through processes that combine metallurgy with what can only be described as applied quantum mechanics, demanding expertise that exists nowhere outside of Brotherhood research facilities. The limited production capacity for ultrasight power armor reflects both the rarity of ultrasight deposits and the extraordinary technical requirements for successful integration of alien materials into functional armor systems. The Brotherhood can produce only a few suits per year, making ultrasight armor among the rarest protective systems in the post-war world and limiting its deployment to the most critical operations and elite personnel. The training requirements for ultrasight power armor operation exceed those of conventional power armor platforms due to the unique operational characteristics created by alien material integration. The armor's protective systems operate through mechanisms that soldiers must understand to utilize effectively, requiring education in quantum mechanics and electromagnetic field theory that challenges even experienced Brotherhood personnel. The psychological effects of wearing ultrasight power armor include sensations that operators describe as otherworldly, as the quantum properties of the alien materials create perceptual experiences that do not occur with conventional armor systems. Some operators report enhanced spatial awareness and intuitive understanding of energy weapon trajectories, though these effects remain unexplained by current scientific understanding. The maintenance protocols for ultrasight power armor are complex and potentially hazardous, requiring specialized facilities equipped with electromagnetic containment systems and quantum stabilization equipment. The alien materials can become unstable if improperly handled during maintenance operations, creating risks that range from equipment failure to potentially catastrophic energy releases that could threaten entire Brotherhood installations. The environmental effects of ultrasite presence in power armor systems extend beyond the immediate protective benefits to encompass broader interactions with post-war, ecological and technological conditions. The crystalline materials appear to influence local electromagnetic fields and radiation patterns in ways that can affect nearby electronic equipment and biological systems, creating both opportunities and complications for armor deployment. The research applications of ultrasite extend far beyond power armor into realms of energy production, weapons development, and theoretical physics that could revolutionize post-war technology if properly understood and controlled. The Brotherhood's scientists view ultrasite armor as merely the first step in a research program that might eventually unlock technological capabilities that exceed pre-war achievements. The strategic implications of ultrasite power armor deployment have influenced Brotherhood military doctrine and tactical planning, as the armor's unique capabilities enable operational approaches that would be impossible with conventional equipment. The enhanced energy weapon resistance makes ultrasite armor particularly valuable against technologically advanced opponents who rely on directed energy systems rather than conventional firearms. The intelligence gathered from ultrasite research has provided the Brotherhood with insights into materials, science, and physics that extend far beyond immediate military applications. The alien materials represent a window into technological possibilities that human civilization had never previously considered, offering potential solutions to problems that had been considered insurmountable with terrestrial technology. The ethical considerations surrounding ultrasite utilization include questions about humanity's right to exploit alien materials whose origins and purposes remain unknown. Some Brotherhood members have expressed concerns that ultrasite integration represents a form of technological contamination that could have unforeseen consequences for human development and post-war recovery efforts. The stability concerns associated with ultrasite armor operation require constant monitoring and maintenance to prevent quantum cascades or dimensional instabilities that could have catastrophic effects extending far beyond individual armor failures. The Brotherhood has developed extensive safety protocols for ultrasite handling, but the alien materials continue to present risks that are not fully understood or controllable. The field performance of ultrasite power armor has proven exceptional in the limited engagements where it has been deployed, with the armor's energy weapon resistance enabling tactical approaches that would be suicidal with conventional protective systems. The armor has demonstrated effectiveness against energy weapons that can penetrate traditional power armor, validating the risks and investments associated with ultrasite integration. The technological spin-offs from ultrasite research have influenced other Brotherhood projects and research programs, as the insights gained from alien material integration have applications extending throughout their technological development efforts. The knowledge gained from ultrasite studies has improved understanding of quantum mechanics, electromagnetic field theory, and materials science that benefits multiple research initiatives. The diplomatic implications of ultrasite power armor possession have affected the Brotherhood's relationships with other post-war factions, as the armor represents technological capabilities that cannot be matched through conventional research and development. The armor has become a factor in strategic calculations and alliance considerations throughout the post-war political landscape. The preservation of ultrasite deposits has become a strategic priority for the Brotherhood, as the limited nature of alien material sources makes conservation essential for long-term research and development programs. The organization has established extensive security protocols for protecting ultrasite mining sites from potential exploitation by hostile factions or unauthorized research efforts. The reverse engineering attempts undertaken by other factions to understand ultrasite technology have proven unsuccessful, as the alien materials require specific containment and stabilization systems that cannot be replicated without access to Brotherhood research data and specialized equipment. The technological barriers to ultrasite utilization have maintained Brotherhood monopoly over alien material applications. The scientific mysteries surrounding ultrasite continue to challenge Brotherhood researchers despite years of intensive study, as the alien materials exhibit properties that appear to contradict established scientific principles. The ongoing research programs represent some of the most advanced scientific work being conducted in the post-war world, pushing the boundaries of human understanding into previously unexplored realms. The long-term implications of ultrasite integration into human technology remain unknown, as the alien materials may have effects that extend beyond immediate protective applications. The Brotherhood's commitment to ultrasite research represents a calculated risk that could either advance human civilization or create unforeseen complications for post-war recovery efforts. The legacy of ultrasite power armor extends beyond its immediate military applications to encompass broader questions about humanity's relationship with technology that originates beyond terrestrial boundaries. The armor represents both achievement and uncertainty, demonstrating human adaptability while raising questions about the wisdom of incorporating alien elements into human technological systems. The rarity and exclusivity of ultrasite power armor have made it a symbol of Brotherhood technological superiority and research capability, representing achievements that validate their institutional mission of preserving and advancing pre-war technology through whatever means become available. The armor embodies the organization's commitment to pushing beyond conventional limitations in pursuit of technological transcendence. The operational doctrine developed around ultrasite power armor deployment emphasizes careful resource management and strategic deployment, recognizing that the armor's rarity makes each suit a valuable asset that cannot be easily replaced. The limited availability of ultrasite armor requires tactical planning that maximizes the armor's unique capabilities while minimizing risks to irreplaceable equipment. As we contemplate the implications of ultrasite power armor, we encounter technology that challenges our understanding of the boundaries between human achievement and alien influence. The armor represents humanity's first successful integration of extraterrestrial materials into protective systems, demonstrating adaptability while raising questions about the consequences of incorporating alien elements into human civilization. In the crystalline depths of ultrasite integration, we find reflected both humanity's capacity for technological transcendence and its willingness to embrace the unknown in pursuit of survival and advancement. The armor stands as testament to the Brotherhood's commitment to pushing beyond conventional limitations while serving as reminder of the mysteries that continue to challenge human understanding in the post-war world. The story of ultrasite power armor teaches us that technological advancement sometimes requires embracing the alien and unknown, that progress may demand integration of elements that challenge our fundamental assumptions about the nature of reality itself. In the armor's quantum properties and otherworldly capabilities, we encounter technology that bridges the gap between human achievement and cosmic mystery. The Hellfire power armor represents the Enclave's philosophy of specialized dominance taken to its logical extreme, embodying a design approach that sacrifices versatility for overwhelming superiority in specific operational parameters. Born from the realization that post-war battlefields would increasingly feature enemies equipped with advanced energy weapons that could neutralize conventional power armor advantages, Hellfire armor emerged from Enclave research programs dedicated to creating protective systems that could not merely survive energy weapon attacks, but thrive in environments where such weapons dominated tactical considerations. The development of Hellfire armor began during the early phases of Enclave technological reconstruction, when captured Chinese plasma rifles and salvaged laser weapons from pre-war military installations, demonstrated that energy-based weaponry would play an increasingly important role in post-war conflicts. Enclave military analysts recognized that conventional power armor, despite its impressive capabilities against kinetic weapons, remained vulnerable to sustained energy weapon attacks that could penetrate traditional protective systems through focused thermal damage. The philosophical approach that guided Hellfire development represented a fundamental departure from the balanced protection paradigm that had characterized previous American power armor programs. Rather than attempting to optimize defensive capabilities across multiple threat categories, Hellfire armor was designed to achieve absolute supremacy against energy weapons, while accepting reduced effectiveness against conventional kinetic attacks as an acceptable trade-off for specialized superiority. The materials science breakthroughs that enabled Hellfire construction required extensive research into thermal dissipation, energy absorption, and heat-resistant composite materials that exceeded anything attempted during pre-war power armor development. The armor's distinctive appearance resulted from the integration of specialized heat dissipation systems and energy-resistant materials that gave the suits their characteristic black and orange coloration while providing unprecedented protection against directed energy attacks. The thermal regulation systems incorporated into Hellfire armor represent some of the most sophisticated environmental control technology ever developed for personal protective equipment, featuring multiple layers of heat-resistant materials, active cooling systems, and energy dissipation networks that could manage the enormous thermal loads generated by sustained energy weapon bombardment. The cooling systems utilized closed-loop heat exchangers that could maintain comfortable internal temperatures even when external surfaces reached temperatures that would melt conventional materials. The energy-resistant plating that forms Hellfire's primary protection utilizes composite materials that were developed through decades of post-war research into advanced ceramics and polymer science. The armor's surface incorporates reflective elements that can redirect laser energy while featuring absorption materials that can safely dissipate plasma discharges through controlled thermal distribution across the armor's entire surface area. The specialized power systems required for Hellfire operation consume significantly more energy than conventional power armor platforms due to the constant operation of active cooling systems and energy dissipation networks. The fusion cores used in Hellfire armor feature enhanced output capabilities and improved thermal management that enable sustained operation under the extreme conditions that the armor was designed to encounter and survive. The psychological impact of Hellfire armor on both wearers and opponents is profound, as the suit's intimidating appearance and distinctive energy weapon resistance capabilities create confidence in Enclave forces, while generating fear and tactical uncertainty in enemy personnel. The armor's ability to walk through energy weapon fire that would instantly destroy conventional protective systems has psychological effects that extend far beyond its practical defensive capabilities. The training requirements for Hellfire operation exceed those of standard power armor platforms due to the specialized systems and unique operational characteristics that distinguish the armor from conventional designs. Enclave training programs for Hellfire operators include extensive education in energy weapon tactics, thermal management procedures, and specialized combat techniques that maximize the armor's unique advantages while compensating for its limitations against kinetic weapons. The tactical doctrine developed around Hellfire deployment emphasizes aggressive assault operations in environments where enemy forces rely heavily on energy weapons, with Hellfire-equipped units serving as breakthrough forces that can penetrate defensive positions that would be impossible to assault with conventional equipment. The armor's energy weapon resistance enables tactical approaches that appear suicidal to observers unfamiliar with Hellfire capabilities. The manufacturing challenges associated with Hellfire production are among the most complex in post-war power armor development, requiring precision fabrication techniques and specialized materials that exist nowhere outside of Enclave research facilities. Each Hellfire suit requires hundreds of hours of skilled labor using equipment and materials that represent the pinnacle of post-war manufacturing capability. The limited production capacity for Hellfire armor reflects both the extraordinary technical requirements for its construction and the specialized nature of its applications, with the Enclave producing only small numbers of suits for elite units and critical operations where energy weapon resistance is essential for mission success. The rarity of Hellfire armor makes each suit a strategic asset that requires careful allocation and tactical employment. The Tesla coil variant of specialized Enclave armor represents a different approach to energy weapon countermeasures, incorporating active electrical defense systems that can disable incoming energy attacks while providing offensive capabilities that transform the armor into a walking electrical weapon system. The Tesla armor features prominent electrical coils that generate defensive fields capable of disrupting enemy electronics while delivering devastating electrical attacks to nearby opponents. The electromagnetic pulse capabilities integrated into Tesla armor create tactical advantages that extend beyond direct combat to encompass electronic warfare applications, as the armor's electrical systems can disable enemy equipment, disrupt communications, and neutralize electronic targeting systems through localized electromagnetic effects. The armor effectively creates a mobile electronic warfare platform that can function independently in hostile electronic environments. The power requirements for Tesla armor operation are substantial, as the electrical generation and field maintenance systems consume enormous amounts of energy, while requiring fusion cores that have been specially modified to support high-output electrical systems. The power management challenges associated with Tesla armor have limited its deployment to specialized applications where its unique capabilities justify the increased logistical requirements. The advanced combat armor variants developed by the Enclave represent refinements of X-01 technology that incorporate lessons learned from extensive post-war combat experience, while pushing the original design concepts to their full potential through sustained research and development efforts. These variants feature enhanced protection, improved reliability, and specialized capabilities tailored for specific operational requirements. The Mark II Advanced Combat Armor represents the pinnacle of Enclave armor development, incorporating improvements that address every limitation identified in previous designs while pushing protective capabilities to levels that exceed anything achieved by pre-war power armor programs. The Mark II features enhanced materials, improved systems integration, and specialized modifications that create the most capable individual protective system ever developed. The environmental variants of Enclave armor include specialized configurations designed for operation in extreme conditions that would be lethal to personnel wearing conventional protective equipment. These variants feature enhanced radiation shielding, improved chemical protection, and environmental systems that enable operations in contaminated zones, underwater environments, and other hostile conditions that require specialized protective capabilities. The stealth variants of Enclave armor incorporate advanced camouflage systems and sound dampening technology that can render the wearer nearly invisible to conventional detection methods while maintaining full power armor capabilities. The stealth systems utilize active camouflage that adapts to surrounding environments while featuring noise suppression systems that eliminate the mechanical sounds normally associated with power armor operation. The command variants of Enclave armor feature enhanced communication systems, tactical data processing capabilities, and battlefield coordination equipment that transform individual soldiers into mobile command centers, capable of controlling complex military operations. The command armor includes secure communication networks, tactical display systems, and data analysis capabilities that support strategic and tactical decision-making. The maintenance requirements for specialized Enclave armor variants are extensive and require facilities equipped with advanced diagnostic equipment and specialized repair capabilities. The complex systems integrated into these armor variants demand expert technicians and specialized parts that exist only within Enclave logistics networks, making field maintenance challenging and requiring careful operational planning. The battlefield performance of specialized Enclave armor has proven exceptional in the limited engagements where these systems have been deployed, with each variant demonstrating superiority in its intended operational role while maintaining compatibility with Enclave tactical doctrine and logistics systems. The specialized capabilities have enabled operational approaches that would be impossible with conventional power armor. The technological spin-offs from specialized armor development have influenced other Enclave research programs and technological development efforts, as the innovations required for specialized armor applications have found uses in other military systems and civilian applications. The research has advanced understanding of materials, science, electrical engineering, and systems integration that benefits multiple development programs. The strategic implications of specialized Enclave armor deployment have influenced post-war military planning throughout the wasteland, as other factions recognize that these specialized systems represent capabilities that cannot be countered through conventional means. The armor variants have become factors in strategic calculations that extend far beyond immediate tactical considerations. The intelligence value of specialized armor technology extends beyond immediate military applications to encompass the manufacturing techniques, materials science, and systems integration knowledge required for their construction. The armor represents preserved and advanced technological knowledge that could influence broader post-war reconstruction efforts if properly understood and applied. The preservation of specialized armor technology has become a strategic priority for the Enclave, as the knowledge and capabilities represented by these systems are irreplaceable and essential for maintaining technological superiority over potential adversaries. The organization has established extensive security protocols for protecting specialized armor research and production facilities. The ethical implications of specialized armor development include questions about the concentration of advanced military capabilities and the appropriate use of such overwhelming technological advantages in post-war conflicts. The armor raises fundamental questions about power, responsibility, and the social effects of dramatic technological disparities between different human communities. The psychological effects of operating specialized armor variants include both positive and negative aspects, as the enhanced capabilities and protection provide confidence, while the isolation and responsibility associated with such powerful systems can create stress and adjustment difficulties for operators. Enclave training programs include psychological support and counseling services for specialized armor personnel. The cultural significance of specialized Enclave armor reflects both admiration for technological achievement and concerns about the concentration of such capabilities in organizations with questionable motivations and methods. The armor represents the complex legacy of post-war American technological development and the challenges of managing advanced capabilities without appropriate institutional oversight. The research applications of specialized armor technology extend beyond military uses to encompass scientific investigation, environmental monitoring, and exploration activities that require protection against extreme hazards, while providing specialized capabilities for data collection and analysis. The armor systems have potential civilian applications that could benefit post-war recovery efforts. As we reflect on the achievement that specialized enclave armor represents, we see technology that embodies both the highest aspirations of protective engineering and the deepest concerns about technological concentration and militaristic applications. The armor demonstrates what can be accomplished when unlimited resources meet brilliant minds in pursuit of specialized superiority, yet raises questions about the wisdom of creating capabilities that far exceed those available to other human communities. In the specialized systems and advanced capabilities of enclave armor variants, we encounter technology that has transcended the limitations of pre-war design while creating new categories of capability and responsibility that challenge our understanding of appropriate technological development in post-apocalyptic society. The armor stands as testament to human ingenuity, while serving as warning about the consequences of unchecked technological advancement. The legacy of specialized enclave armor extends beyond immediate military applications to encompass broader lessons about the relationship between technology and human society, demonstrating that advanced engineering capabilities must be balanced against social and ethical considerations that determine whether technological achievement serves human flourishing or creates new forms of oppression and inequality, enmeshing the ongoing struggle for post-war recovery and civilization. The T-65 power armor stands as the most paradoxical achievement in post-war technological development, a suit that matches the statistical capabilities of its pre-war predecessors, while representing something infinitely more precious, proof that human civilization possesses the resilience and ingenuity necessary to create rather than merely scavenge, to innovate rather than simply preserve, to build new foundations, rather than endlessly repairing the crumbling remnants of a world that died in nuclear fire 2 centuries ago. The origins of T-65 development trace back to the Secret Service's remarkable institutional survival through the Great War and its aftermath, representing one of the most extraordinary examples of governmental continuity in the face of civilizational collapse. While most federal agencies dissolved into chaos or were vaporized along with their headquarters, the Secret Service maintained operational capabilities through a network of secure bunkers, underground facilities, and hardened command centers that had been designed to ensure government continuity under the most extreme circumstances imaginable. The preservation of technical expertise within Secret Service ranks during the post-war period required deliberate policies and institutional structures that prioritized knowledge retention over immediate survival concerns, a strategic approach that distinguished the organization from most post-war communities that focused exclusively on short-term survival at the expense of long-term capability development. The Secret Service maintained libraries, technical manuals, manufacturing equipment, and most importantly, educated personnel who understood the complex systems required for advanced technology development. The decision to pursue power armor development represented a strategic calculation by Secret Service leadership, who recognized that protecting government interests and personnel in the post-war environment would require capabilities that exceeded anything available through conventional means. The development program reflected institutional understanding that effective governance in the wasteland required not just political authority, but technological superiority that could ensure the physical security of government operations The engineering challenges associated with developing entirely new power armor technology using post-war resources were staggering, requiring innovations in materials, science, manufacturing techniques, and systems integration that pushed the boundaries of what should have been possible, given the limited industrial capacity available to any post-war organization. The Secret Service somehow managed to maintain or recreate the sophisticated production capabilities required for precision power armor manufacturing. The materials science breakthroughs that enabled T-65 construction utilized both preserved pre-war knowledge and genuine post-war innovations, creating hybrid technologies that combined the best aspects of pre-war materials with improvements that had been developed through 2 centuries of post-apocalyptic research and experimentation. The armor incorporated lessons learned from extensive study of existing power armor platforms while pushing beyond their limitations through original research. The manufacturing processes required for T-65 production represent perhaps the most sophisticated industrial operations conducted in the post-war period, requiring precision fabrication techniques, quality control procedures, and systems integration capabilities that existed nowhere else in the wasteland. The Secret Service maintained production facilities that rivaled pre-war military contractors in their technical sophistication and manufacturing precision. The design philosophy that governed T-65 development emphasized reliability, maintainability, and operational effectiveness, rather than the experimental approaches or specialized applications that had characterized other post-war power armor programs. The armor was designed as a practical tool for professional government personnel who needed dependable protection rather than experimental subjects for pushing technological boundaries. The servo motor systems integrated into T-65 armor feature improvements over pre-war designs that reflect 2 centuries of accumulated knowledge about power armor operation and maintenance under field conditions. The servos incorporate refinements that address common failure modes, improve reliability under stress, and simplify maintenance procedures, while providing performance characteristics that match or exceed pre-war standards. The power management systems built into T-65 armor demonstrate sophisticated understanding of fusion technology and energy distribution that enables efficient operation while supporting the armor's advanced systems. The power systems incorporate automatic optimization protocols and energy conservation features that extend operational duration beyond what was achieved by pre-war power armor platforms. The armor plating used in T-65 construction combines pre-war materials science with post-war innovations in composite manufacturing, creating protective systems that provide balanced defense against multiple threat types while maintaining reasonable weight and mobility characteristics. The plating incorporates lessons learned from extensive study of power armor performance under various combat conditions. The heads-up display technology integrated into T-65 helmets represents genuine post-war advancement in battlefield information systems, incorporating processing capabilities and sensor integration that exceeded most pre-war power armor platforms. The displays provide comprehensive tactical information through user interfaces that reflect 2 centuries of experience with power armor operation. The environmental protection systems built into T-65 armor are specifically designed for post-war conditions, providing enhanced protection against radiation, chemical contamination, and biological hazards that are more prevalent in the wasteland than they were in pre-war battlefields. The filtration and life support systems incorporate understanding of post-war environmental threats that enables effective operation in contaminated zones. The modular design philosophy that characterizes T-65 construction enables extensive customization and upgrade potential while maintaining compatibility with standard components and systems. The armor's modularity reflects understanding gained through centuries of power, armor, maintenance, and modification, creating platforms that can be adapted for different operational requirements without compromising basic functionality. The acquisition process for T-65 armor represents one of the most demanding resource accumulation challenges in the post-war world, requiring participants to demonstrate sustained commitment to challenging objectives while accumulating rare materials and specialized components through complex trading networks and dangerous exploration activities. The process serves as both procurement method and qualification system that ensures only dedicated and capable individuals gain access to the technology. The Treasury Note system that governs T-65 acquisition reflects sophisticated understanding of post-war economics and resource management, creating incentive structures that encourage productive activities while providing mechanisms for allocating rare resources to individuals who can utilize them most effectively. The system represents genuine innovation in post-war economic organization and resource distribution. The gold bullion trading mechanism that forms the foundation of T-65 acquisition demonstrates institutional understanding of stable value systems and long-term economic planning that distinguishes the Secret Service from TAIN. Most post-war organizations that operate on subsistence, economics, and immediate resource consumption. The bullion system creates stable value storage that enables long-term planning and investment. The vendor relationships required for T-65 acquisition involve complex networks of suppliers, traders, and specialists who maintain the economic infrastructure necessary for advanced technology distribution in the post-war world. These relationships represent remarkable achievements in post-war commerce and demonstrate the persistence of sophisticated economic systems despite the collapse of conventional governmental and corporate structures. The grinding mechanics associated with T-65 acquisition serve multiple functions beyond simple resource accumulation, creating educational processes that teach participants about post-war economic systems, resource management, and the complex networks of relationships required for advanced technology access. The process transforms participants into sophisticated post-war economic actors who understand the true costs and values of advanced technology. The daily quest systems that support T-65 acquisition encourage sustained engagement with post-war economic and social systems while providing structured activities that contribute to broader community welfare and resource generation. The quest systems create productive incentives that benefit both individual participants and broader wasteland communities. The event participation requirements for T-65 acquisition foster cooperation and social interaction among participants, while providing mechanisms for large-scale resource generation and community-building activities. The events create shared experiences that build social bonds and mutual support networks that enhance post-war community resilience. The faction activity integration that characterizes T-65 acquisition encourages participants to engage with broader post-war political and military organizations while contributing to collective objectives that extend beyond individual power armor acquisition. The faction systems create larger purposes and social identities that give meaning to individual efforts and resource accumulation. The crafting requirements for T-65 construction teach participants about advanced manufacturing techniques and materials science, while providing hands-on experience with the complex processes required for power armor production. The crafting systems preserve and transmit technical knowledge that might otherwise be lost while creating deeper understanding of the technology being acquired. The material gathering challenges associated with T-65 construction require participants to develop comprehensive understanding of post-war resource distribution, scavenging techniques, and trading networks while building practical skills in resource management and logistics planning. The material requirements create educational experiences that enhance participant capability and knowledge. The plan's acquisition process for T-65 construction involves complex relationships with specialized vendors and requires significant resource investments that demonstrate participant commitment while ensuring that advanced technology remains accessible only to individuals who have proven their dedication and capability through sustained effort and resource accumulation. The modification systems available for T-65 armor enable extensive customization that reflects individual operational requirements and tactical preferences, while maintaining compatibility with standard components and systems. The modification options demonstrate the armor's flexibility and adaptability, while providing mechanisms for continuous improvement and specialization. The maintenance requirements for T-65 armor are manageable with proper knowledge and resources, though the sophisticated systems require understanding of advanced technical concepts and access to specialized tools and materials. The maintenance systems reflect the armor's design emphasis on practical utility rather than experimental complexity. The performance characteristics of T-65 armor in operational conditions demonstrate the effectiveness of post-war engineering and manufacturing capabilities, while validating the resource investments required for acquisition. The armor's battlefield performance matches pre-war standards while incorporating improvements that reflect centuries of accumulated knowledge and experience. The psychological impact of T-65 ownership extends far beyond the armor's practical capabilities to encompass feelings of achievement, capability, and connection to advanced technological systems that represent the best of post-war human achievement. The armor provides confidence and identity that enhance individual effectiveness while creating social recognition and status. The social implications of T-65 ownership include both positive and negative aspects, as the armor creates distinctions between individuals who have access to advanced technology and those who rely on conventional equipment. The social effects require careful management to prevent the creation of technological elites that undermine community cohesion and mutual support. The economic impact of T-65 acquisition extends throughout post-war trading networks and resource systems, creating demand for specialized materials and services, while providing incentives for productive activities and skill development. The economic effects demonstrate the armor's role in supporting broader post-war economic development and technological advancement. The educational value of T-65 acquisition processes teaches participants about advanced technology, economic systems, and social organization, while providing practical experience with complex resource management and planning activities. The educational aspects create lasting benefits that extend far beyond individual power armor ownership. The preservation aspects of T-65 technology ensure that advanced manufacturing knowledge and technical capabilities are maintained and transmitted to future generations, rather than being lost through the gradual decay that characterizes most post-war technological systems. The preservation efforts create foundations for long-term technological recovery and advancement. As we contemplate the achievement that T-65 armor represents, we see technology that embodies hope for humanity's continued advancement, despite the devastating setbacks of nuclear war and civilizational collapse. The armor demonstrates that human creativity and determination can overcome seemingly impossible challenges when properly organized and persistently applied to constructive objectives. In the sophisticated systems and genuine innovation of T-65 armor, we find proof that the post-war world possesses the capability for technological renaissance rather than mere preservation of pre-war achievements. The armor represents the first steps toward rebuilding human civilization on foundations that may eventually exceed the accomplishments of the world that was lost in nuclear fire. The story of T-65 development teaches us that institutional continuity and preserved knowledge can enable remarkable achievements, even under the most adverse circumstances, that human societies can maintain and advance technological capabilities through deliberate policies and sustained effort, despite the collapse of the broader civilization that originally created such capabilities. The experimental power armor variants that emerged from the deepest research facilities and most secretive laboratories of the post-war world represent humanity's willingness to push beyond conventional boundaries of technology and biology, creating protective systems that challenge fundamental definitions of what power armor should be and what the human body can become when fused with technologies that blur the lines between mechanical augmentation and biological transformation. These variants embody the desperate creativity and moral ambiguity that characterize post-war scientific research, conducted without the ethical oversight and institutional constraints that had limited pre-war experimentation. The Strangler Heart power armor stands as perhaps the most disturbing and fascinating example of post-war technological experimentation, representing a convergence of power armor, engineering with botanical sciences that creates protective systems incorporating living plant matter as integral components of defensive and offensive capabilities. The armor emerged from research programs that explored the potential for integrating post-war flora with mechanical systems, seeking to create hybrid technologies that could adapt and evolve in ways that purely mechanical systems could never achieve. The botanical integration that characterizes Strangler Heart armor requires the cultivation of specialized plant organisms that have been genetically modified to interface with mechanical systems while maintaining their biological functions and adaptive capabilities. The plants exist in symbiotic relationships with the armor's mechanical components, drawing power from the suit's fusion systems, while providing organic defensive capabilities that can respond to threats in ways that conventional armor cannot replicate. The living armor concept that underlies Strangler Heart design represents a fundamental philosophical departure from traditional power armor engineering, embracing biological processes and organic adaptation as essential components of protective systems, rather than merely incorporating biological elements as supplementary features. The armor exists as a genuine fusion of organic and mechanical systems that creates protective capabilities through biological as well as technological means. The growth patterns exhibited by Strangler Heart armor enable the suits to adapt their protective characteristics over time, developing enhanced resistance to specific threat types through biological processes that mirror evolutionary adaptation but operate on much shorter timescales. The armor can literally evolve improved defensive capabilities through exposure to various attacks, creating protective systems that become more effective through combat experience. The maintenance requirements for Strangler Heart armor include both traditional power armor technical procedures and biological care protocols that involve feeding, watering, and nurturing the living components that form integral parts of the protective systems. The armor requires operators who possess both technical expertise and botanical knowledge, creating unique training requirements that exist nowhere else in power armor applications. The psychological effects of wearing living armor create unique challenges for operators who must adapt to the sensation of wearing protective systems that are literally alive, growing, and responding to environmental stimuli in ways that can be both comforting and deeply unsettling. The biological components of the armor create sensations of warmth, movement, and organic responsiveness that distinguish the experience from conventional power armor operation. The ethical implications of Strangleheart technology raise profound questions about the appropriate boundaries of biological experimentation and the moral considerations involved in creating hybrid life forms that serve military and protective functions. The armor represents technology that challenges conventional distinctions between tool and organism, between equipment and living being, creating philosophical dilemmas that have no precedent in human experience. The prototype power armor variants discovered in various research facilities throughout the wasteland represent experimental approaches to power armor design that were abandoned before completion due to technical challenges, resource limitations, or the intervention of the Great War that ended most research programs before they could achieve their intended objectives. These prototypes provide insights into the developmental paths that power armor technology might have followed under different circumstances. The experimental servo systems incorporated into various prototype armor configurations explored alternative approaches to strength augmentation and mechanical assistance, including hydraulic systems that operated at higher pressures, electromagnetic actuators that provided more precise control, and hybrid biological-mechanical interfaces that attempted to integrate organic muscle tissue with mechanical components to create enhanced strength capabilities. The advanced sensor packages integrated into prototype armor variants included experimental technologies that pushed the boundaries of battlefield information systems, incorporating synthetic aperture radar, quantum entanglement communication systems, and biological neural interfaces that could provide direct mental control over armor systems through thought processes rather than physical manipulation of controls. The exotic power systems explored in prototype armor research included fusion variants that achieved higher energy densities, experimental antimatter containment systems that promised virtually unlimited power generation, and biological energy harvesting systems that could derive power from the wearer's own metabolic processes or environmental energy sources such as radiation and heat. The materials science experiments conducted in prototype armor development explored the potential for incorporating exotic materials and manufacturing techniques that exceeded the capabilities of conventional power armor production, including programmable matter that could reconfigure its properties in response to threats, self-repairing materials that could heal damage automatically, and quantum-scale engineering that operated at molecular levels. The neural interface systems developed for prototype armor applications attempted to create direct mental connections between operators and armor systems, enabling thought-controlled operation that could respond faster than conventional manual controls, while providing sensory feedback that allowed operators to experience their environment through the armor's sensor systems as extensions of their own senses. The adaptive armor concepts explored in various prototype programs investigated the potential for creating protective systems that could modify their characteristics in real time to optimize defense against specific threats, including armor that could alter its density, flexibility, and energy absorption properties through automated systems that analyzed incoming attacks and adjusted protective parameters accordingly. The modular construction experiments conducted with prototype armor systems explored more extensive customization potential than conventional power armor platforms, including systems that could be completely reconfigured for different mission requirements through rapid component exchange, armor that could be assembled from interchangeable parts to create entirely different protective configurations. The environmental adaptation systems integrated into prototype armor variants were designed to enable operation in extreme conditions that exceeded the capabilities of conventional power armor, including armor configured for underwater operations, space environments, extreme temperature conditions, and high radiation areas that would be instantly lethal to personnel wearing conventional protective equipment. The weapon integration systems developed for prototype armor applications attempted to create more sophisticated interfaces between armor and weapon systems, including armor that could mount integral weapon systems, energy projection capabilities built directly into armor components, and targeting systems that could coordinate multiple weapons through unified fire control systems. The communication systems explored in prototype armor research investigated advanced networking capabilities that could create mesh networks between multiple armor units, quantum entanglement communication that could not be intercepted or jammed, and biological communication systems that utilized organic processes to transmit information between operators. The life support systems incorporated into prototype armor variants explored more advanced environmental protection capabilities, including closed-loop atmospheric recycling that could sustain operators indefinitely, biological filtration systems that could process any atmospheric contamination, and medical systems that could perform surgical procedures automatically to treat injuries sustained during operations. The stealth technology integrated into prototype armor configurations investigated various approaches to concealment and detection avoidance, including active camouflage systems that could render armor invisible to visual observation, electromagnetic signature suppression that could defeat electronic detection systems, and quantum stealth technology that operated through manipulation of probability fields. The mobility enhancement systems developed for prototype armor applications explored alternatives to conventional walking and running locomotion, including integrated flight systems, teleportation capabilities that could move operators instantaneously across short distances, and dimensional phase technology that allowed armor to pass through solid barriers. The manufacturing challenges associated with prototype armor production exceeded the capabilities of conventional industrial systems, requiring precision fabrication techniques, exotic materials, and quality control procedures that pushed beyond the limits of available technology. Many prototype systems remained incomplete due to manufacturing limitations rather than design flaws. The testing procedures required for prototype armor validation involved extreme conditions and dangerous experimental protocols that exceeded normal safety standards, reflecting the experimental nature of the technology and the urgent military requirements that drove development programs beyond conventional risk assessment parameters. The abandonment of prototype armor programs due to the Great War left numerous incomplete research projects and partially developed systems scattered throughout research facilities, creating opportunities for post-war discovery and potential development by organizations with sufficient technical capabilities and resources to continue the research. The reverse engineering efforts undertaken by post-war organizations to understand prototype armor technology have yielded mixed results, as the incomplete nature of most prototype systems makes functional reconstruction difficult without access to the original research teams and complete technical documentation. The preservation of prototype armor research represents significant challenges due to the experimental and often unstable nature of the technology, requiring specialized storage conditions and maintenance procedures that exceed the capabilities of most post-war organizations, while presenting potential safety hazards. The integration potential of prototype armor technology with conventional power armor systems offers opportunities for incremental advancement that could improve existing platforms without requiring complete reconstruction of established designs and manufacturing capabilities. As we contemplate the experimental variants and prototype systems that represent the furthest reaches of power armor development, we encounter technology that pushes beyond the boundaries of conventional engineering into realms where science, biology, and imagination converge to create possibilities that challenge our understanding of what protective systems can become. In the living systems and exotic technologies of experimental armor variants, we find reflected both humanity's limitless creativity and its willingness to explore territories that may be too dangerous or ethically problematic for responsible development, demonstrating that the pursuit of technological advancement sometimes leads to discoveries that we are not prepared to control or fully understand. The legacy of experimental power armor research extends beyond immediate military applications to encompass broader questions about the appropriate limits of human technological development and the wisdom of pursuing capabilities that may fundamentally alter the nature of human existence itself, reminding us that innovation without wisdom can create opportunities that become threats to the very humanity we seek to protect. The legacy of powered protection stretches across the wasteland like shadows cast by giants, each suit of armor telling stories of human determination, forged in the crucible of necessity and refined through decades of struggle against forces that sought to extinguish the flame of civilization itself. From the desperate scrap metal wielded by raiders seeking any advantage against the harsh realities of survival, to the technological marvels that represent humanity's greatest achievements in protective engineering, these mechanical shells have sheltered us through the darkest chapters of our species' journey toward recovery. In the quiet contemplation of armor's evolution, we see reflected the entire arc of human adaptation. Our capacity to transform tools of war into instruments of peace, our ability to preserve knowledge through the collapse of empires, our determination to build tomorrow from the ashes of yesterday, each servo motor that still functions, each fusion core that still glows, each piece of composite plating that still deflects harm, stands as testament to the enduring partnership between human ingenuity and mechanical precision that has carried us through 2 centuries of trials. Rest now, guardian of the wasteland, and dream of the watchers who stand vigilant in their shells of steel and circuitry. Let the gentle hum of power systems and the steady rhythm of servo motors carry you toward peaceful slumber, knowing that somewhere in the darkness, someone keeps watch over the innocent in armor that represents humanity's refusal to surrender hope to the forces of entropy and despair.